Okay, yeah, so it's 7 o'clock, guys. I think I'll go ahead and get started. I'm so glad you're here. Thank you for taking the time to come by. I hope this will be a helpful session. Before I actually get into the math, I just want to kind of give you my game plan for my schedule. So if you're thinking you want to ask me some questions and whatnot, um, I'm going to do this session. Probably is going to go till about 9:30. If you need to leave early, no problem. I understand. You'll just stay for whatever you want to do. But I'll be here basically doing this session till about 9:30. After that, I'm probably going to take a short break just for myself, kind of rest my voice for a few minutes or whatnot, and maybe even go get a snack again because I eat a lot. And then I'll come back and I'm going to have office hours. I'm probably going to stay till midnight tonight. So if anybody has any energy left or you have any more questions after the session, you're welcome to stick around. The building gets locked at 10 p.m. from the outside. But if you're inside the building, nobody comes down and kicks anybody out of that room by my office. So you can kind of just hibernate down there and you shouldn't have any problems at all. So you're welcome to do that. About midnight, I'm probably going to go home if I'm still standing by that time. I should get in tomorrow around 8. That's as much of a morning person as I can be. That's doing pretty good if I can do that. If you come right at 8 tomorrow morning to ask me questions and I'm not there, it probably means I'm racing over. I slept in too long or something, but I'll get in as soon as I can. So if there's any last minute questions, you can ask me. I really don't have anything else I have to be doing between now and tomorrow when you're going to take the test. So this is my main priority is to help get you guys ready. Hopefully for the exam, you're going to feel pretty good. And I just want to be as available as I can. So, yeah, and hopefully, if you haven't had a chance to try a sample exam yet, I would definitely say that as soon as the session is over and maybe you want to take a little break as well, but then I would try to take a look at some of those problems. Even tonight would be good. I know, some people don't want to stay up so late, but just so you have a little bit of time. If you look at that sample test and you realize, oh, there's still some things I need to review, you don't want to put yourself in a position where you don't have any time left to do any reviewing. But I also just really want to recommend that you do try to get some rest. I know that I can still go on like 3 or 4 hours of sleep. I've still been known to do that occasionally. I go hiking. I get up sometimes at 3 in the morning to do that. But it's not a great thing if you don't get any rest tonight. So try to get yourself some rest so that you will feel sharp and fresh in the morning. I think that's actually almost more important than trying to pull an all-nighter just studying like crazy. That would be my personal opinion. You know yourself better than anybody else how you could handle that and what you're going to do. Anyway, I am going home at midnight to get some sleep. I'll probably be back around 8 o'clock tomorrow. Okay, so that's my schedule. And I am recording this session. I will send this out as a video in case anybody does need to leave early and you want to see the rest of what we covered. Yesterday, I sent out the video from yesterday's session. As it turned out, I had to send out 2 links because I had a problem with my battery on my phone. And so hopefully tonight I won't have the same problem. But anyway, you might have had a chance to watch that already, or maybe you didn't. What I'm going to do tonight is I'm going to start with some problems that I did not cover yesterday in the session. I actually got through most of the problems already yesterday, but I'm going to start with the ones that I didn't talk about yesterday. They're from the review session and from some of these handouts. And then I'm going to go back to the ones that I already did yesterday. And so I see some of you were here yesterday. Also, if you start realizing this looks like a rerun, you can certainly step out. You don't have to stick around for that. Does that sound okay? I also really want to point out, I talked about, there's chapter 6, 7, 8, and 9, and that they would be about equally represented on this midterm. That is true. Keep in mind, though, that chapter 9 heavily uses chapter 7. The eigenvalue, eigenvector material is heavily used when you're solving those systems of differential equations. We certainly saw that. So you ought to be thinking, oh man, that's like half the exam. Half the exam is going to be matrices with eigenvalues, eigenvectors, systems of differential equations, both non-defective and defective. That's a big chunk. That's really a big chunk. So I'm actually going to start tonight with one of the chapter 9 problems that I didn't get a chance to do yesterday. I'm going off of the review session handout. So if you're trying to reference it with the resources folder, that's where you can look. And I'm not going in order here. So I'm going to number them for you so that if you want to match them up later to what's in the Canvas page, you'll be able to do that. All right. So let's start with this problem right here. So this is, I'll just call this midterm 3 practice. And I'm going to the review session questions here. And I'm going to start with number 4 from that review session packet. So that's why it's out of order, is because I'm jumping around. This is one of the ones I did not do yesterday. So what it says, guys, is solve the initial value problem. That's sometimes just abbreviated IVP. And the initial value problem of x prime equals a times x. So this is the $1 million equation of chapter 9, right? Where capital A is the matrix given by -2, -1, 4, and then 0, -1, and 0, and then -1, -3, and 2, with, and then I'm going to give you the initial value here. This is x of 0, which would be the vector -2, 1, and 1. Okay, so this would be a good question that I could ask you to solve. All right. And so we recognize right away that this is a system of differential equations. It's a 3 by 3 system. That means that the solutions to this system forms a 3-dimensional subspace. And that means I need to find 3 basis solutions. 3 basis solutions. And that's usually done through the eigenvalue eigenvector pairs. This was the amazing thing we learned, guys, in chapter 9. One of the big revelations of this chapter is that the eigenvalues and eigenvectors of A are somehow related to finding the basis solutions to this system. If this wasn't the case, we probably wouldn't even have this class. You wouldn't talk about linear algebra and differential equations together. So when you see a problem like this, just realize you're really putting the topics together nicely, okay? So the first step is going to be, as always with this, is to find your eigenvalues. And it is so important to get these eigenvalues right, because otherwise everything just goes sideways on you. It just, nothing really, the calculations don't make sense if you're not using the right eigenvalues. Yeah, so let's see if we can do this. By the way, great turnout. I love this. It's like almost a whole class worth right here. It's fantastic that you guys were able to come. I'm really, really glad for that. Okay, so to do the eigenvalues, just remind everybody here, we do this determinant. Okay, and I have to subtract the lambda off of the main diagonal. So -2 minus lambda, -1 and 4. And then on the second row, 0, -1 minus lambda, and 0. And then on the bottom row, I have -1, -3, and 2 minus lambda. Okay. And how do you suppose we're going to tackle that determinant? Brandon? Exactly. We're going to do cofactor expansion. I want to scan through my matrix. If I see a nice row or column with zeros in it, I want to take advantage of that. So in this case, I would definitely suggest that we expand on row 2. Okay? So we'll expand on row 2 because I have 0 for the first term, 0 for the last term, and it's really only the middle term that I'm going to have to keep track of here. So I have the middle term, which is -1 minus lambda. If I cross off that row and column, I'm going to set up some brackets here and write down the 2 by 2 minor that we get when we cross off the middle row and column. So it's going to be something like this. Remember that, guys, parentheses are your friend here. Really try to use those to help you with the algebra, yeah? So if we use these nice brackets, we have this 2 by 2 minor, which will be only a quadratic equation in those brackets, okay? Remember, the last thing you want to do is to multiply it out. Don't do that. If you multiply this all the way out, you're just going to get a cubic equation, and you might be able to solve it still, but it's just harder than it needs to be. It's already partially factored. Let's take advantage of that. This -1 minus lambda in the front is already there for me to use. What I'm going to do instead is take the part that was the minor of the cofactor expansion and go ahead and treat that as a quadratic equation, and I can multiply out just in the brackets to figure out what that equation is. So if I do that, I see a lambda squared here, and then plus 2 lambda and minus 2 lambda, that cancels. And then -4 plus 4, oh, that also cancels. This is actually the whole thing. This is the whole thing, and I need to set this one equal to 0. All right? And if I do that, what are my lambdas here, guys?
0, 0, -1.
Exactly, 0 and 0 and -1. Now, I always recommend, because it's so important to get this right, I recommend that you double check that with the fun facts, just to be sure. If you take the trace of this matrix, the diagonal should add up to what your lambdas add up to. So -2, -1, and 2, that adds up to -1. That looks good, right? The other thing you could do is take the determinant of A. Remember that the fun fact for this is that the determinant of A is the product of the lambdas. So notice that the product of the lambdas is 0. So if you took the determinant of this matrix, you should get 0. And you will actually. If you cofactor expand the middle row just of this matrix, the minor that goes with the outside corners of this matrix is actually a determinant of 0. So it does work. So it's good to confirm that. That way you have the peace of mind that you know that you have your lambdas right. Do we know if this matrix is defective or not defective yet? We don't actually know that. If there were no repeats, if none of the lambdas were repeating, then we could say confidently that there's no defective possibility, right? It would definitely be non-defective. Because there's a repeat here, it's possible that this is defective. We don't know yet. We're going to have to check it by calculating the eigenvectors that go with these eigenvalues to see if these eigenvalues pull their weight. Yes.
And if the lambdas were on distinct from each other, would you still want us to check it? Or can we just write it off as?
Well, you would know it's not defective. You don't have to say anything else. But the point is, you're still going to have to solve the problem. But you would know that it was be non-defective in that case. Yeah. Okay. So I'm going to leave you in suspense for a minute about whether it's defective or not. I'm going to work with the eigenvalue that did not repeat. Sometimes if the question is just asking you whether it's defective or not, I probably would start with lambda equals 0, because that's the one that really is the crux of the matter. But since I know I have to do all of these eigenvalues anyway, I'm just going to start with this one just to kind of get it over with. Okay, so there will be a null space that we have to calculate for this. And I'm going to subtract -1 from the main diagonal of my matrix. That means I'm basically going to add 1 to the main diagonal of my matrix, and it's just going to give me this little matrix here. So just adding 1 to the main diagonal only. Everything else about this matrix is just the same as what we had before. So adding 1. Now remember that this matrix never can be invertible. It can't be, because you had been setting your determinant equal to 0 when you solved for that lambda. So this determinant cannot be 0. Must be 0. It cannot be an invertible matrix. Now I'm going to go ahead and do an ERO or two here. I'll take the first row and just take the negative of it. And then let's just move the third row up to the middle row. And the all 0 row, I'll just recopy it down here on the bottom. Okay? This is where you got to be real careful too, guys. Okay? A lot of times I see people going a little fast and making mistakes on these EROs. And that has big consequences for like what kind of calculations you're going to get. So just be careful here. That first row has a pivot in the top left corner, but then I'm just going to add the first row to the second row. Just add the first row to the second row, get 0, -2, -1, and the rest of it just stays the same, like so. And now, let's see. I've got my X, my Y, and my Z here. And Z is a free variable. Let's just call it T. And then I'm just gonna kind of do the back substitution process. So for the middle equation, negative 2y minus z is adding up to 0. If I solve that for y, if I solve this one for y, I would move the 2y to the other side probably, and then divide by 2. It's negative 1/2 of z. So in other words, y is negative 1/2 of t, as it turns out. Go ahead and put that in there. And then I have to go to the first equation, which is x plus y minus 4z equals 0. Honestly, what all of this is doing right now, guys, is something from chapter 2. We learned how to solve these kinds of systems way back in February. And so it goes without saying, I expect people to be doing this by now. So just be careful with it. It's easy enough to make a mistake if you're not careful. So I'm going to try to solve this one now for x, right? So let's just do it over here. X would be equal to 4z minus y. If I solve isolating for x, 4z minus y. And then I can put in t where I have a z. And then where I have a y, I can put minus 1/2 of t. So it's just 4t minus negative 1/2 of t. And if you work all of that out, I believe it's just 9/2 of t. So that's going to be x. If I didn't make a mistake, it should be 9/2 times t. Okay? Once I've got my unknowns in terms of my free variable, all I have to do is make my vector. And I'll call this vector v1. I make my vector by busting out the variable. So in this case, I have to bust out the t, and I get 9/2, negative 1/2, and 1. Okay? So far, so good. So even though this problem is from chapter 9, all of the work I have done so far is stuff that really belongs with chapter 7. So I keep saying these two chapters really blend together. The only part of this that's really from chapter 9 is when we now take the eigenvalue, eigenvector pair and build a solution. So I'm going to build the first solution right here. It would be called x1 of t. And this one would be e to the negative t times the vector 9/2, negative 1/2, and 1. Okay? So there's your first solution. And that takes care of the first lambda. Yeah,
Is it all right if we simplify the vector?
okay, so when you say simplify it, you mean like get rid of the fractions? That is totally okay. If you take a scalar multiple of an eigenvector, you get another valid eigenvector. So if you don't like fractions, if you don't want to deal with these fractions, you could double everything. So you'd have 9, negative 1, and 2, and that would be fine. Yeah, absolutely fine. The reason that that's fine, by the way, is because if you scalar multiply this vector by a scalar, when we finally get to the general solution, there'll be a C1 in front of this term. And that C1 is allowed to be any scalar as well. So it kind of absorbs the scalar into the C1 in that case. Yeah, okay. So far, so good. In this one problem, we can review a lot of the material because we have all of this chapter 7 stuff. And now we're also going to be solving, of course, the chapter 9 stuff, which is what the question really looks like. Let's go to our other eigenvalue now, which is 0. It's kind of a weird eigenvalue to have, but that is a possibility. In this case, you are literally just going to take the null space of the matrix as is, because you're subtracting nothing from it, right? You're just subtracting 0 from the main diagonal. Remember, this matrix cannot be invertible. If you did EROs on it, you would have to get a row of zeros somewhere. And so we may as well just go ahead and cross off a row. I talked about it in my review session yesterday. I'd like to reiterate this for you guys today because people sometimes wonder, oh, can I just cross off any row that I want? If I had this matrix here, this is exactly the example I used yesterday as well. If I had this matrix here and I told you that this matrix is not invertible, and that you would be able to cross off a row, right? All of that is true. But if you come along and decide to cross off that row, you have actually not gotten rid of the dependency of the two rows, right? So don't just do this randomly. How do you know if you've made a good choice of what row to cross off? Here's a simple answer. The simple answer is that if it's a 2 by 2 matrix, it doesn't matter. You can cross off either row that you want on a 2 by 2. For a 3 by 3, the way you'll know that you are safe and that you did a good choice of a row to cross off is that the two rows that you did not cross off should not be multiples of each other. Like here, after I crossed off a row, the other two rows were multiples of each other. That's a problem. That's a problem. So what you have to make sure is that whichever row you cross off, the other two rows are not multiples of each other. Then you will know that you've removed the dependency, so to speak. So the other thing is you usually want to try to cross off a row that's messy. I would not cross off the middle row here. I would keep that middle row. That middle row is simple. It's going to be easy. It's going to be really, really helpful. So keep the middle row and then keep one of the other two rows. I kind of like having this one here. So let's go ahead and cross off the first row. And then let's just do that little check. Are the two rows that we did not cross off, are they not scalar multiples of each other? Answer is they are not, right? They are not scalar multiples of each other, which means that crossing the first row is a good choice. All right. So just to get this looking a little nicer, I'm going to move the bottom row to the top. I'll also do a sign change on those values. And then I'm going to keep the middle row where it is, but I'm going to do a sign change there as well. And my row of zeros, normally we always like to put that at the bottom. So this becomes the matrix that you have. And by the way, do we know yet whether this is going to be defective or not defective?
It's going to be defective.
It is going to be defective. It absolutely is, because I only have one free variable, which means when I bust out the free variable, I'll only get one eigenvector, which is not pulling its weight, which was 2 over here, right? So it's going to be a defective system. So here's our setup for that, x, y, and z. Z is free. I'll go ahead and call that one T. And then if I look at the middle equation just tells me that y is equal to 0. It's 1 times y equals 0. So y is equal to 0. And then going to the top equation, if I just write it out for a second, it's x plus 3y minus 2z equals 0. But we already know that y is 0, so that part won't matter. And if I solve for x, it's just going to be 2z, which would be 2t once I've done it in terms of my free variable. So there are your x, y, and z values, and we can make our vector here, I'll call it v2, which is the eigenvector 2, 0, and 1. Right, so we busted out the t, and this is the eigenvector. We got one eigenvector, but it's not enough because my lambda has a weight of 2. Yeah, please.
And then those eigenvalues, like those vectors, would be part of the subspace of the eigenspace?
Yep, this is a basis for the eigenspace corresponding to lambda equals 0. That's absolutely right. So what is my second solution? I can actually go ahead and write it down. The general form of it, I'm just going to put this here since I didn't write it on the board yet tonight, but I think everybody knows that the general form of your solutions in chapter 9 is e to the lambda t times v. You want to make sure you've got that down, right? E to the lambda t times v in that box. In this calculation, the lambda is 0. So if the lambda is 0, then you just have e to the 0 here, which is 1. So you just get the vector, right? So your second solution is actually just literally this vector, 2, 0, and 1. I'm going to go ahead and put a box on that one as well. Okay, so far so good? Now the thing is, we need 3 solutions. We need 3. We've only got 2 on the board so far in the boxes. I need a third solution. And because we know that A is defective, we have an eigenvalue that did not pull its weight, so it's a defective matrix. That means that we have to, sorry. Did you have a question?
No.
Okay, that means we have to do the thing with the W's that we learned just this last Thursday, right? So on Thursday, I explained this W process. Let me just remind you that my third solution is going to look like the form of e to the lambda t times W1 plus t times W2. So this is the form of it. Now already we know that lambda is 0. E to the 0 will be 1. So this part's going to kind of go away. We're not going to have to think about the exponential for this problem. But how do we do the W business? Okay, so I know we just learned this a few days ago, but it's really not that bad if you just remember this diagram. So I start with W1, I hop across the arcs of this picture to get to W2, and then I hop across the arc of that one to get to the 0 vector. Okay, so there you go. That's the picture that you need to know for this case. By the way, in class last week, when we have a defective system, we learned we kind of put them into 3 types. There was what I liked to call the mixed eigenvalue type. There was the regular defective type, and then there was the super defective type. In class last Thursday, I did an example of the super defective one and also the mixed eigenvalue one. And in the homework, I think all 3 of them showed up at least one time. So you've hopefully had a chance to at least get 4 or 5 times to practice this. We're going to do once more right here. You're always choosing this W1. In this case, we are talking about mixed eigenvalue, right? Sorry, I forgot to finish my little comment there. This is a mixed eigenvalue defective system. It's called mixed eigenvalue. So I'm going to choose this W1. How do I choose it? I choose it so that it will survive 1 power of a minus lambda I, but not 2 powers. Now, in this case, lambda is 0. We're still in this eigenvalue of 0. So when I write a minus lambda I here, I really just mean a. So what I would recommend that you guys do, we already have a on the board there. I would recommend that we go ahead and calculate a squared, because that would be 2 powers of my matrix, which is corresponding to 2 arcs of this picture here, okay? So I'm just going to write down the A matrix twice, okay? So everybody feel okay with matrix multiplication? The range of mistakes that people can make is so varied. Like sometimes people will just make typos with the EROs or with the determiners. So I can totally live with that. What I really don't live with very well is 15 weeks into the semester and people can't multiply a matrix. So make sure you know how to do this matrix multiplication. We have to do dot products of the rows of the first matrix with the columns of the second matrix, just dot products, okay? So just be patient with yourself. We want to get this right. We want to try to get this right. So just go slow and careful. Okay, so in the upper left corner, I'm going to have 4 plus 0 minus 4. So that's 0. And then on the top middle, I have 2 plus 1 minus 12. 2 plus 1 minus 12 is negative 9. And then in the top right corner, I have negative 8 plus 0 plus 8, which would be 0. Now I'm going to go to the second row and do the same dot products again. 0 plus 0 plus 0. And then in the middle, I have 0 plus 1 plus 0. And then in the right middle entry, I have 0 plus 0 plus 0, which is, again, 0. Okay? And now let's go to the bottom row. On the bottom row, guys, I have 2 plus nothing minus 2. That would be 0. And then in the middle entry, I have 1 plus 3 minus 6. That's negative 2. And then finally, the far bottom right corner is negative 4 plus 0 plus 4, which actually is just 0 again. So this is a squared. The key thing here, okay, so guys, if you're in the super defective case, this last matrix you calculate will be all zeros, which actually is nicer than what we have here. In the mixed eigenvalue case, you will often get a matrix here that is not all zeros. And why is that a big deal for us? Well, it's because when we choose this W1, now we're gonna have to tread carefully with this, because I have to choose a W1 that is going to not survive this matrix, but that will survive that matrix, right? Okay, so let's see if we can make a choice here. Anybody want to try me on one? Okay, so if we go with 1, 0, 0, that's often the first thing that comes into my mind is to try that one. If we do this, then we can figure out what W2 is, because W2 is just, so keep in mind, guys, from this diagram, W2 is just, it's just A times W1, yeah? It's just going to be A times W1. And because we chose such a nice, simple W1 vector, then when you multiply by A, what happens is you just pick off the first column of A. In other words, you're just going to pick off this first column of A, and it's going to give you what I just circled there, which is -2 and 0 and -1, like so. Yeah, that's it. And then, is it true that this W2 will not survive this matrix? That is true, because what happens when I put 1, 0, 0 next to this guy? Well, I pick off that, don't I? Well, that's all zeros. That's what we want, right? We want to end up at 0 here, guys. After we take 2 powers of A, we want to get 0 when we apply that to our vector. But do be careful, because it would not have been okay to choose 0, 1, 0. 0, 1, 0 would have given you, right here, would have given you this vector, which is not 0, 0, 0. Okay, so just be cautious. In fact, the one that I did in the lecture last Thursday, we actually couldn't choose any of the standard R3 basis vectors. We had to create something that was even a little bit more creative than that, because every column had some non-zero entries in it. So it's just a case-by-case situation. In this case, we can get away pretty easily with just 1, 0, 0. But it won't always work out quite like that. Okay, so I've got my W1, I've got my W2, so now I can write down my x3 of t. x3 of t is coming from here. The exponential part is gone because lambda is 0. On this problem, lambda is 0. And so what I'm going to have is W1, which is 1, 0, 0, plus t times W2, which is -2, 0, and -1. Also, just a quick, another quick reminder, this W2, it has to be an eigenvector of the matrix. If you go back and refresh your memory what the eigenvector was that we had found when we did this null space a few minutes ago, we got 2, 0, and 1. Well, look what we came up with here for our W2. It's literally just a multiple of that eigenvector, which is another eigenvector. That actually should be reassuring to us. Like, okay, yes, the W2 looks like it's an eigenvector. It's just a multiple of the one we calculated already. Yeah. Okay, is everybody with me? So this is another example of the mixed eigenvalue case. And let me write down now the final general solution to the system, okay? See if we can write it down nicely here. Let me move my camera again. Trying to get a decent video here. So let's see if we can write down x of t is equal to c1 times my x1 right here, which is e to the -t times 9/2, -1/2, and 1. Okay. And then plus c2 times x2, which is 2, 0, and 1. And then plus C3 times X3, which we just wrote down over there, 1, 0, 0, right? Plus T times -2, 0, and -1. Yeah, that's the whole general solution. Yeah. Caesar first and then Brandon.
And if we decided to do the zeros first, do we kind of mix that order of that?
Yeah, the order of these terms makes no difference. So if this was your first term and this was your second term and this was your third term, it's just as good as what I wrote down there. Yeah. Do you have a question as well?
Yeah, so you said that if we already, like, if we marked x1 of t, x2 of t.
I know where you're going with this.
we could
Yes.
just write down the general solution basically.
Okay, so I know what you're saying, and I'm really glad you brought this up. It would be totally okay, you would get full credit if for your answer right here, you just wrote down C1 times x1 plus C2 times x2 plus C3 times x3, because, you know, this is usually going to be less writing than what you have up there. So that would be totally okay. However, there's a however coming. This problem is actually an initial value problem, meaning that we are not done yet. If it just said find the general solution, I would totally just do this and I wouldn't bother to write the whole thing out. However, because they gave us an initial value, the purpose of that initial value, what it's going to do for us is going to allow us to solve for the constants. Well, I'm not going to be able to do that if I've just written this kind of abstract expression here. What I really would need to do to really solve for the constants is get my teeth into this general form with all of the functions plugged into it. So Brandon's making a really good point. Normally, I would have just done this because it's faster, easier, you can't really mess it up. The only way you can mess it up is to forget to put the constants in there. Somebody did that on the take-home quiz. But for the most part, it's a straightforward thing to just throw those constants in front of those terms. The only reason to write it all the way out again is if you've got more work to do. And in this case, we do. I think, Aaron, you might have had a hand that was.
Oh, I was just gonna ask, is the depth of whatever you do in the Jordan chain is based on what they're saying?
This is not the Jordan chain. This is not, I never called it a Jordan chain. This is my little trick diagram for how to remember the W process for the defective case. So section 9.5, I went away from the book and I did it in a streamlined way for 3x3 matrices. If you had only one, if you had a super defective matrix, by super defective, I mean the same lambda 3 times, and you only managed to get one eigenvector for that lambda, then as we talked about on Thursday, you would have a W3, W4, and W5 in addition to this, and you would have to use that. And that's a bigger diagram than the one right here. Yeah. Usually the way I play this game, by the way, guys, is I put one of them on the midterm, and whichever one I didn't do, then in the final I do that one. Just to let you know. So like there's 3 different types. You're probably going to see a defective system tomorrow. And then you're probably going to see another one the following week. So make sure you know all of these 3 types. In this case that we're doing right now, we don't need the W3, 4, and 5. We don't need it because this one is not super defective. Yeah.
I don't, at least not yet. I don't feel comfortable choosing a W1, like the whole guessing. Like the whole objective is for it to survive for W2 and then to.
And then to die after we do the squared power. Yeah.
Right.
So what you want to do, if you're sitting there frozen on the test, you're like, oh my gosh, I can't remember how this works. It's kind of complicated. What I would do to get yourself unstuck is just start calculating the powers of A minus lambda I. So you've already got A minus lambda I written down. In this case, it's the same as A because lambda was just 0. But A minus lambda I, write it down. Square that matrix, right? And if it's super defective, cube the matrix also. Right? So you calculate those powers and then you're saying, then you'll have all those matrices in front of you. You've got A, you've got A squared, and you're saying, okay, what vector could I set next to that matrix that would, so that it would be killed by that matrix, but not killed by that matrix.
And
that takes practice, and there's not just one right answer.
Yeah, and then would you want to choose your W1 based on like the multiplicity of the lambda?
Not really. No,
Oh.
it has more to do with just, I want a vector that will not survive this matrix, but that will survive that matrix. And that's like a wordy way of basically explaining the diagram. So if you draw, this is the other thing you guys should do. I will give you partial credit if you just draw this diagram and you're like, I don't know what to do with it. But if you draw the diagram, I will say, okay, they at least know it's a defective system and they're supposed to be using this diagram. This is another great way to get yourself unstuck. Draw this diagram and then calculate the A minus lambda I and its powers. Okay, most of that you can do without really like breaking a sweat with like what the W's are going to be. Just get the diagram up there and calculate those matrix multiplications. Every little bit that you do is worth credit towards this solution. This is going to be like a 12-point problem. This is a big deal. It's like a letter grade difference, honestly, to get this one right. So you really want to be on top of this. Now, we're not done yet. We're not done yet. You guys are asking really good questions, and so I'm still looking here at just the general solution. I have to use my initial condition. So just to show you that part of it, a lot of times I don't do initial conditions, but for this one, I decided I'd go ahead and do it. You just have to plug in 0 here, right? So you plug in 0 for t. And everywhere I see a t, I'm just putting 0. Well, in that case, I just have c1 times 9/2, -1/2, 1, plus c2 times 2, 0, 1, and then plus c3 times 1, 0, 0. And t is 0 everywhere in what I wrote down. And we're setting that equal to what they gave us over there, which was -2, 1, and 1. Right. Okay, so there you have it. And this is just one vector equation, but this is enough to solve for the constants. If I read across the top slot of everything I see, I'm going to have 9/2 of C1 plus 2 C2 plus C3 equals -2. And then if I go to the middle slot, right, on the middle slot, if I read across, I have -1/2 of C1 plus nothing equals 1. And then if I read across the bottom slot, so just top, middle, and bottom here, guys, the bottom slot is C1 plus C2 is equal to 1. Okay? I would probably just, I mean, you could put this into a matrix and put a smile on my face solving it with EROs and stuff, but we can do this one a lot more easily. If we just take this middle equation, you can solve for C1 immediately. It's just -2. It's just -2. And once you know that, you can solve for C2 from the bottom equation. If C1 is -2, then C2 should be 3. And then once I know that C1 is -2 and C2 is equal to 3, I should be able to solve for C3 as well. Let's see if I can do this in my head. 9/2 of -2, that's -9 plus 6. So that's so far -3. I have to add something to it in order to get to -2. That would be a 1. So C3 should be 1. I think I did that right. I didn't. I'm sure somebody will correct me, but that should be C1, C2, and C3. And so then my final answer is going to be to just take the general solution and stick these numbers in. If you didn't actually do that because you're like, I'm bored, I've already written this down and I don't want to rewrite this again, you could just kind of like, you could just do something like this. Your whole goal, guys, is to show me that you know the material. If you did something like that, I would know that you knew what you were doing. Okay, so I would be okay with that instead of recopying it all again. Save yourself some time. Yeah. Okay, so this is a big deal. This is a lot to it. We had to do all the eigenvalues, the eigenvectors. It was a mixed eigenvalue defective case. And it's definitely one of the cases that you need to know. And this is the one that I personally think is the hardest one. Just because the A squared matrix here was not just zeros. Questions on this? Anything else for the time being? Andrew.
So I know this was brought up earlier with
Okay.
like the spectrum, like I'm 2 and -1 on the 2 and then 1.
Yes.
So if I turn that into like,
If you doubled it.
yeah,
If you doubled it, what would happen is the C1 would come out half as much. So that you have the same answer, right? Like if So we solved it and we got C1 to be -2, right? But if you had decided originally, no, I'm gonna go ahead and double everything, so you would have this. Then what would happen when you solve for your constants is you would have only gotten -1 there. So it would have compensated for the fact that you doubled the vector in the first place. Now you would have a constant that was half as much, but honestly, it's the same answer. Yeah, does that make sense?
Yeah.
Great question. Yeah, that's a good question. Okay, anything else on that? Yeah, Dart?
When we're doing this, like the defective cases, we don't put an X for the repeated vectors.
That's right, so it's easy to get mixed up between chapters 8 and 9. Chapter 8 is where you're not dealing with vectors at all. In chapter 8, you've got things that look like scalars, like e to the rx. And if there was a root, some root r that got repeated up here, then when you're writing down the general terms of your solution, you start stacking those x's. And so this X stacking business that we learned about in the chapter 8, that does not apply at all in chapter 9. There is no X stacking. So just be careful about that. It's a really good question. There's usually some folks that get a little mixed up about that. So yeah, Kim?
When I do the test, how I differentiate like the difference between that one and the other one? That was the difference.
You mean like super defective versus mixed eigenvalue?
Yeah.
That comes through going through each of your eigenvalues and seeing how many eigenvectors they're producing. So if you go back to your notes from Thursday, I actually wrote all 3 cases. I made a little kind of 3-column thing. And the mixed eigenvalue was one of the columns, and then I had the regular defective in another column, and then the super defective in another column. It all comes down to just the eigenvectors that you're creating from each eigenvalue. That's how you figure it out. Yeah, this one I know it's mixed eigenvalue because I don't have the same lambda 3 times. It's not the same lambda 3 times. Yeah. Does that make some sense? Okay, yeah, Aiden.
Can you just remind me why it would be like way easier if it zeroed out when we multiply the matrix?
If the whole thing zeroed out, because if the whole thing zeroed out, then any vector would have died right here. As it is, the vector 0, 1, 0 would not have died. And so that would have been a bad choice because you want this vector to get killed by this power of this matrix. But if this matrix is all zeros, then you almost don't even have to think. It's just like, oh, any vector will work for making it die here. You still have to make sure that it survives the previous power of the matrix though, right? So, but instead of having to juggle 2 things, which is what we're having to do right now, you only have one thing you really have to pay attention to. Yeah, it's a really good point. Okay, anything else for the moment on that? Okay, well, we reviewed a lot of stuff in that one problem. Let's go on to something else that I did not go over on the last review session. Just going to knock out 1 or 2 more things from that, and then we're going to go back to the problems that I did last night and just kind of repeat some of those. This one is off of group work. This is one from the group work that we didn't ever have a chance to do. So this is from group work 12, is problem number 1. Okay, I'm jumping around, and it's a different topic completely from what we were just doing. But basically what we want to do is assume that A, B, and C are distinct numbers. Distinct numbers just means they're not repeating each other. And then what we're going to be asked to do is to show that the set of e to the ax, e to the bx, and e to the cx is linearly independent. We're going to try to show this one. So this is off of the group work. Unfortunately, I didn't have enough time to do this group work with you guys in class. It would have been a good one to do, but we'll just do it now. First thing you notice about this is, oh, there's no matrices, there's no vectors. These are just scalar expressions. These look like these must be the roots of some auxiliary equation, right? Because we've learned that, you're building solutions of the form e to the rx, where the r's are the different roots. So let's imagine that we had 3 distinct roots. Now, normally when that happens on the homework or on any examples that we did, I never stopped us and said, oh, let's stop and check that they're Li. It's because I knew that this was already true. We don't usually have to do this. What I'm trying to say for your practical value is, if I don't say on the test to show that the vectors that I'm giving you are Li, then you don't need to do it. You don't need to bother with it. We're just going to assume that it works. You remember those 14th order differential equations that we had? Oh, we're not going to do a calculation that those 14 vectors are Li. That's way too hard. Computationally, it's way too hard. So this would be about as tough as it could get. You got 3 vectors here. You got to see if they're Li. What is the go-to approach for showing that these functions are Li? It's the Wronskian. Very good. Yes, so we're going to do the Wronskian. I'll remind you guys that there are 2 different versions of the Wronskian. There's one from chapter 8, and there's one from chapter 9. But the W test, which is how you actually test for Li, is the same for both of them. The actual test itself is the same, but the way that you set up your W matrix, your Wronskian matrix, is different if you have scalar functions compared with vector functions. So in this case, the way you do this, remember, it's a determinant, and just make sure I give myself enough room here. It's going to be important to just lay the original functions right out into the top row of your matrix here. So e to the ax, e to the bx, e to the cx, right? You just lay those there. Now, if these were vector functions, if they were vectors, guys, they would actually fill up the entire matrix already. You'd already have your W fully written out. And that's the way chapter 9's Wronskian works. You don't even have to do anything else. You just lay the vectors there. For us, this is a chapter 8 problem, by the way. This is from chapter 8. You have to do this problem by now taking derivatives down the matrix here. So if I pull the derivatives out, I'm just going to pull the constants down, right? So a e to the ax, b e to the bx, and c e to the cx, like that. And then I have to do it one more time because it needs to be a square matrix before I can go any further. So I'll pull another factor of a down, another factor of b down, and another factor of c down. And it's going to look like that. This is my Wronskian. It's just this 3 by 3 determinant. And if we want to show that these functions are Li, well, this is kind of nice. They already told us that they're Li. That means that there must be some way. The way the W test works is that you should be able to plug a number in for x. I like to call it x naught. You should be able to plug a number in for x that will make this determinant not 0. Right? The W test, how does it work? If this determinant is not 0, then the functions are Li. And we know that they're supposed to be. Now, I think the one on the sample midterm, so some people were right outside my office working on it right before the review, didn't say, show that the functions are Li. It asked you, are they Li or LD? And we did not know. So if you look at the sample test, you're going to find a problem that's like this, but it was more of a up in the air question. If it's up in the air, then you have to accept the fact that it's possible that you're going to start trying to plug numbers in here and you're never going to win, right? You're never going to get a non-zero Wronskian. And after you've maybe tried twice or so to win this game, maybe you can't get it to work, you might have to actually pivot to the conclusion that maybe these functions are actually LD. And in that case, that's something different, right? But for Li, if they've already told us to show that the functions are Li, we just have to plug in a number here. What's the best number to plug in, do you think?
0.
How about 0? I usually would use 0 if I can, okay? Now, if I do that, I'm gonna get the determinant of, so e to the 0 is just 1, so I have a 1, a 1, and a 1. And then on the second row, all of these exponentials go away, I just have a, b, c. And then on the third row, I just have a squared, b squared, and c squared. And we just wanna try this out, maybe it'll work, maybe it won't. I would probably do this determinant using the arrow method. So the arrow method, if you remember from way back in chapter 3, you just recopy the first 2 columns of the matrix, and then we just have to draw these diagonals. So we'll get, BC squared for the first diagonal, and then the next diagonal is plus CA squared, and then the next diagonal is AB squared. And then we start doing minus, right? Then we have minus the diagonal that goes this way, which is a squared b, and then minus b squared c, and then minus c squared a. And what we are hoping is that we can win this game by convincing ourselves it's not 0. Right, that's the idea, is that this would be not 0. Well, I have to tell you, I don't want to spend too much time on this because when I first did this problem, the very first time I ever did it, I stood here staring at this for the longest time, like, oh, I must be able to cancel something or like group the terms or whatever. And you can try really hard to do that, and it just does not work out very well. It's just not is not going to cancel very nicely. So I'm going to tell you the next step is one that you shouldn't worry about. Like, it's not something that would be something I would throw at you on the test. It turns out that, because it's totally just algebra, this turns out that if you refactor it, there is a clever way to factor it, which is like this, guys. It is b minus a times c minus a times c minus b. Okay, so right there, I'm just going to tell you to trust me on this. If we did this as a group work in class, I would have had this as a hint that, oh, by the way, if you multiply these 2 things out, you'll get all of that. Yeah. So you can, if you don't believe me, okay, I told you to trust me. If you don't believe me anyway, you can just go ahead and FOIL this all the way out, and you will see that it comes out to exactly the terms that I have above that. Now, guys, A, B, and C are all distinct numbers. That means that B minus A is not 0, C minus A is not 0, and C minus B is not 0. None of them are the same, right? So actually, you're multiplying together 3 numbers that are all not 0. And so your W is not 0. This is since A does not equal B, A does not equal C, and B does not equal C. They're all distinct. They're all distinct numbers, so you don't have any chance of canceling anything out there. Those are 3 non-zero values. So this is it. This is all there is. So then you can say, so let's set e to the ax, e to the bx, e to the cx is Li by the W test. By the W test. Yeah, that's the reason. Do I need to write down the W test, or are we okay with this? The W test just says, if you can find a value of x naught such that the W is not 0, then the vectors are then the functions are Li. Yeah. That's the W test. And it's the same W test in chapter 9 when you have vector functions as well. Okay, so somebody came up with this question and verified that anytime you get 3 distinct roots, you can build 3 linearly independent solutions. I'm not going to be asking you to stop and do this showing on every problem, right? We're just going to take these things for granted. So just to repeat myself again, unless I ask you to show that your functions are Li. I probably won't mention the W test. I'm going to expect you to know that. But if I say something like show that these functions are Li, then you should be thinking, I need to do the W test, right? But unless I ask for that explicitly, you don't need to do it. If I give you some big 14th order differential equation and I say find the general solution, you just find all your roots and write down your 14 terms and you move on. Does that make sense? Okay. The problem number 2 on this same group work is actually the proof of the W test. I never actually proved it. I sort of just stated it for you without proving it. I had hoped to do the proof for you. You can see it takes, this is a pretty wordy group work. There's a lot to it. It's like 5 steps that I kind of wrote down here. I think I'm going to skip that just because I'm not likely to ask you something that's that involved that has like 5 parts to it. That's all just a theoretical proof of this W test. The main thing is make sure you know the W test and you can use it, because I might ask you a question that's similar to this. And those of you who've looked at my sample test have already seen that. So anyway, that's the that's the group work number 12. Okay. Any questions on the fun? Doing okay? All right, let me do, I think there's just one more thing here that I didn't do last night. I think I'll do that next, and then I'll start repeating the stuff from yesterday. I have some good problems that we did yesterday that I think some of you might want to see, so I'll get to that. But I just want to do one more thing here first. So let's go. This one is actually from group work number 15. This is the other group work that we didn't get a chance to do in class. The group works for this midterm, guys, are going to be 10 through 15. These are the ones you want to be studying. And by the way, I've been talking to people who have been studying these. These are good to look at. So we did group works 11, 13, sorry, 10, 11, 13, and 14. We did all of those in class. Those would be good to look at. But 12 and 15, we just ran out of time. So what is this problem number 1 here? This is just going to say, consider the system. So what is it? X1 prime of t equals negative 6x1 plus x2. And then x2 prime of t is equal to 6x1 minus 5x2. And the question, there's 2 parts here. Part A is going to ask us to, actually, sorry, there's 3 parts here. The first part is, the question is, what is the fundamental matrix for this system? Before I write down the rest of the parts, let's start with this first part first. What is the fundamental matrix for the system? Now, I have to be honest here as well with this. I mentioned what this fundamental matrix is in passing. We did not harp on it much. I did not go over it a lot. What it is it's really just the matrix that has the solutions into the columns. So you're just going to solve this system like normal. It's a chapter 9 problem. You're just going to solve this system like normal, and then when you get your solutions, you're going to lay them out into the columns of a matrix. That's called the fundamental matrix. So I'm not likely to use this word on the test tomorrow, but just so you know what it is, it's just the matrix that has the solutions in it. I'm more likely to just say, what is the general solution for the system? That would be a more familiar question. Okay, so it's basically the same thing. I'm basically asking for the same thing. The first thing you need to do here, guys, is what do you suppose is the first thing you're going to want to do here? I don't think that's the first thing I would do.
Form the matrix.
Put it into a matrix. Like this is a system that should probably be written as a matrix, right? So this is actually just x prime equals a times x. And when you're writing down what the matrix A is, This matrix I'm writing down, by the way, is not the fundamental matrix. Fundamental matrix is later when we actually get the solution. This is just the coefficient matrix for my system. And to write it down, you literally just grab the numbers out of this problem, right? And you just don't get fancy, just lay them right in the same order. Okay, so you don't, occasionally I'll get a student who tries to transpose this thing or something. Don't do that. Just write the numbers exactly as you see them here. Okay, so there you go. It's only a 2 by 2 system. Let's go ahead and find our eigenvalues. This one I'm going to do it kind of fast, guys. -6 minus lambda and 1, and then 6 and -5 minus lambda. It's a 2 by 2 determinant, so I think we can all handle that. It's just going to give me a quadratic equation here in a minute. I'm using my AD minus BC formula for the determinant. And so we have -6 minus lambda times -5 minus lambda minus 6. All right, and if I FOIL that out, I'm going to get lambda squared. And then my cross term is 6 lambda plus 5 lambda. That should be 11 lambda, right? And then I have 30 minus 6. Well, that comes out to 24. And we're going to be setting this one equal to 0. So in a second, we will try to find the lambda values. Let me give myself a little bit of room here. Okay. So if you can't factor this easily, you always have the quadratic formula to fall back on. Okay, so don't get freaked out with quadratics. You should always be a-okay. Just use the quadratic formula. This one does factor nicely, though. You probably realize already that 24, we can break it up as 8 and 3. It's going to be a nice way to do that, because then when I put a plus between those terms, I get my 11 lambda as a cross term. So it's exactly what we wanted. And so I get my lambda. My first lambda is -8. My second lambda is -3. I already know that this matrix is not defective. There's no repeat lambdas here. And so that's a good thing. And there's not even any imaginary numbers. So it's actually quite a nice one. The calculation isn't going to get too messy, I don't think. But we can go ahead and I like to sometimes, when it's this simple, I just make 2 columns here. You've seen me do this before, where I just like work out my space for these null spaces. So the first null space here, guys, for lambda equals -8. I have to subtract -8 from the main diagonal, which just means I'm adding 8. So when I add 8 to the main diagonal, I'll get 2 and 1, and then I'll get 6 and 3. This matrix cannot be invertible. It never will be invertible. Cross off a row, we know that has to happen. And I'm going to use this AB trick to write down my eigenvector. My eigenvector, I'll call this V1, is just going to be -1 and 2. When you're swapping the 2 and the 1, you can put the minus sign on either entry. It actually doesn't matter. So I just chose the first one, but it doesn't really matter there. Okay. The other eigenvalue, let's just work on that one while we're at it. We have another null space to do. This time I'm going to subtract -3 from the main diagonal, which in other words means I need to add 3 to the main diagonal. I'll get -3 and 1, and then I'll get 6 and -2. And just as expected, these 2 rows are multiples of each other again. I'll cross off the one I don't want to think about. I'll swap the 2 numbers, the A and the B here. That gives me a 1 and a 3, and I've got my eigenvector there. Okay, let me know if I'm going too fast. So now I'm going to make my 2 basis solutions. Okay, so my first solution, x1 of t, right? This is going to be e to the -8t times the vector -1, 2. And then my second solution, I'll put it right below, x2 of t, right? This is just going to be e to the -3t times the vector 1 and 3. Okay, And just for the purposes of putting this into a matrix, I'm gonna do something that we don't normally do. Normally what you wrote here is just fine. I'm gonna actually shove these exponentials inside the actual vector. So again, this is not normally an extra step that you have to do, but you'll see why I want to do it here in just a second. So that's shoving it in there. I'm gonna also shove it in on the second vector as well. So just shoving the exponential into the slots of the vector, right? And so then my fundamental matrix, in the brief discussion I did of it in class, I called it capital X of T. And what this matrix is you literally just lay these solutions into the columns. Just lay them into the column. So the first vector, negative e to the negative 8t, and 2 e to the negative 8t. And then the second column, e to the negative 3t, and 3 e to the negative 3t. That is your fundamental matrix. Again, I'm not likely to ask you for that. Basically, all it is taking the two individual solutions and laying them into the columns of a matrix. Why am I bringing it up if I'm not going to ask it? And like, what's the big deal about this? Actually, on Thursday in class, we're going to need to make this fundamental matrix for the one last topic that we have left to cover on Thursday. So I might as well give you a preview of that now. So that's my fundamental matrix. And then what is part B? So part A is the fundamental matrix. 95% of this is just the same stuff we've been doing all along. Find the eigenvalues and eigenvectors and build your solutions. Okay. Yeah, part B is to write the general solution. So general solution. Guys, we can already do this. We don't even need to do any more work. We can immediately write the general solution here, yeah, using these two basis solutions. So you guys have seen me do this a lot. This is just x of t equals, right? Go to the final answer. C1 times the first solution. I'll go back to the original version of it here. E to the negative 8t times the vector negative 1 and 2 plus the second term is C2 e to the negative 3t times the vector 1 and 3. So there's your general solution, just like that. And then part C, these are very quick parts. Part C is to classify the phase portrait for this system. I'll probably have a list of options for you. Do you remember what the options are? We got like 6 of them, I think. Saddle, sink, source. There's 2 types of spirals: unstable spiral, stable spiral, and the last one, circle. Okay, which one is it? Sink. It's a sink. Okay, guys, this is a quick, easy question. If I give you a question like this, I'm handing you hopefully an easy one. You just have to look at the lambdas. Both of the lambdas are real and they're both negative. So no imaginary numbers here. They're both negative. This would be a sink. I mean, we could, I suppose I could make everybody mad at me and make you draw the face portrait, because drawing the picture is always tedious. Like, oh, I got to draw this vector negative 1, 2, right? And so you've got this line coming in like that. And then the vector 1 and 3 would be here. It's coming in like that. And you would just imagine dropping a feather into this face portrait. And the feather, if I'm not on those eigenlines, then it might be curved, but the feather will always drift in towards the origin here. Okay, I'm much less likely to ask you to draw the face portrait than I am to ask you to tell me something about it. If you looked at my sample midterms yet, one of the 2 midterms, I think, has an actual matching exercise. So I might have like this matrix and 2 or 3 others, and then I might have 2 or 3 other face portraits. And I say, which matrix goes with which face portrait? So I really like that question. So you'll maybe want to practice that one from the sample test. It's a good. But the thing about it is, it's just coming down to what kind of lambdas you have. So it is something to memorize, but it isn't so bad, right? It's really pretty straightforward. If you get two real eigenvalues, then it's either a saddle, a source, or a sink, depending on whether they're positive or negative. One of each, or two positives or two negatives, and that gives you the three cases. Aiden?
So if we were like presented with like a matching question.
Yeah.
We would just only have to solve for the.
For the lambdas, yeah, you would just, I mean, I could have asked part C right here. It said, okay, classify the face portrait, and we would already know that it's a sink. Yeah, exactly. Does that make sense? Actually, if you really do pull up group work 15, there's a second problem that asks you to just do it again for a different matrix. I think I'll skip it because you guys can do it, and the solutions are posted anyway. But that's the idea behind it. Yeah, this is really, really quite easy. Okay, any other questions on this one? Okay, I am now going to start recycling the problems I did in yesterday's session. So if you were here yesterday, you're going to recognize these problems. And if you feel like you don't want to stay, I will not be offended in the least. Anybody can leave early anytime they need to. Did I tell you about my review sessions when I was a grad student? I did.
Yes.
About how it was like 6 hours and then nobody would leave. And it was like, all they wanted me to do was stop, but I kept thinking they wanted more, and like nobody communicated very well. That was mostly on that was on me. And if I would have just said, hey guys, you think we should quit? We might have gotten out of here. So, but I think it hasn't been 6 hours yet, so I'll go a little longer. Yeah, because I like these problems. So if you didn't stop by yesterday, you might find these to be helpful. So let's go back to the review packet. I'm going to do number 3. So I'm done going over the group works. Now I'm just going back to the review session questions. And number 3 is going to say, find the general solution to, again, here we go, x prime equals a times x, where A is this matrix here, -1, -4, -2, and then -4, -5, -6, and then 4, 8, and 7. So it's a 3x3 system. And as you're writing that down, one of the first things you probably realizing here is that this is not the nicest matrix in the world. There's actually no zeros in it. So I probably would be shooting myself in the foot to put this there, because without a calculator, it would be so easy to get into trouble. You're going to get a cubic equation for the lambdas, and there's no telling how hard it's going to be. So, but what if I do this? What if I give you a hint? Okay. What if I give you a hint, and the hint is going to be that one of the eigenvalues, spell that out carefully, one of the eigenvalues of A is lambda equals 1 plus 2i. So I'm just going to give that as a free hint here. And if I was going to put this on the test, I would have to do that too. I probably would. It would just be such a nightmare. People would be getting the lambdas mixed up because it's just, yeah, I could get it wrong easily. It's just messy. Kim?
So if on the even value is the 1 plus 2i, then the other one would be 1 minus 2i.
Okay, so you're making the first observation. Yeah, did everybody catch that? Yeah. I'm giving you one of the lambdas here. There's a total of 3 lambdas in total, but as Kim said, these complex lambdas, they always come in pairs like this. So if I have 1 plus 2i, I would also have 1 minus 2i. Were you going to say something also?
Yeah, so
please.
then afterwards, can't you add up those ones and then add the third lambda to the trace of it?
Okay, I can't get anything past you guys. You totally have it, right? Basically, if I give you one of the lambdas like this, we can get the other lambdas without breaking a sweat. It's not so bad. So I'm just going to say, so then The second lambda would be 1 minus 2i, right? And then, actually, let's just call this one lambda 1. The first lambda is 1 plus 2i. The second lambda is 1 minus 2i. And then all three lambdas together have to add up to the trace of this matrix. So if I add up the diagonal of this matrix, -1 plus -5 plus 7 adds up to 1. If I take the lambdas that I have so far, the lambdas that I have so far are adding up to 2, right? So lambda 1 plus lambda 2 is 2. So the third lambda, to make the entire list of lambdas add up to just 1, the third one has to be -1. Okay, so these are my lambdas. It's so important to get the lambdas right. I keep saying that. Okay, do we have any repeat lambdas here?
No.
We really don't. There's no repeats. And that actually tells me already that this is going to be a non-defective system this time. It's non-defective, which is kind of nice. It means we don't have to do the thing with the W's. Remember the W1, W2, potentially W3, 4, and 5. We don't have to do any of that because this is non-defective. On the downside, the negative thing about this example is we do have imaginary numbers, and we cannot give answers at the end of the day that have those imaginary numbers in them. So we're going to have to work carefully to get rid of those. Let's start with the easiest lambda first, which is -1. If you don't mind, I just want to get that one done before I get into the imaginary numbers. So for lambda equals -1, I'm going to do a null space here. What I have to do is I have to subtract -1 from the main diagonal, which is like adding 1. So if I add 1 to the main diagonal of my matrix, I'll get 0, -4, -2. And then I'll get -4, -4, -6. And then I'll get 4, 8, and 8. Still kind of messy. But let's remember that we know that we can cross off a row. I probably would not cross off the first row because the first row actually has a 0 that might be useful. I'd cross off one of the other 2 rows. I don't really like all those minus signs, so let's cross off the middle row. That's probably the one that I am the least happy to deal with, so we'll get rid of it. And then what I'm going to do, guys, is one real quick ERO. I'm going to take that bottom row and I'm going to move it up to the top, but I'm also going to cut it down by a factor of 4. So 4, 8, 8 can be cut down to 1, 2, 2. Okay, and then the top row, I'm actually going to cut that one down by -1/4, right? So I'm going to turn that -4 into a 1, which means the -2 turns into a 1/2. So this would be, without a whole lot of effort, we're able to get a pretty good row echelon form going. Figure that out pretty quickly. Kim?
It's gonna be always true, like any of the rows we talked about, equal to 0.
Yeah, you're just, when I cross off a row, it just means it zeroes out.
So like,
And I know it has to happen. It has to happen because this matrix is not invertible. If you take a matrix that's not invertible and you do EROs on it, you must get a row of zeros every time. That's right.
But like you said earlier, it can't be a row that's a multiple.
Right, the 2 rows that are still here should not be scalar multiples of each other. So I don't want you to just blindly cross something off, but most of the time, anything you do is going to be pretty safe. I like to just keep the numbers as simple as I can. Yeah, okay. So guys, what do we have? We have x, y, z. Z is my free variable. As you can see, I'll call that t. And then if I look at the middle row of my matrix, the middle row of my matrix creates this equation right here, right? Y plus 1/2 of z is equal to 0. So if I solve that for y, I'm going to get -1/2 of t for y. Okay. And then I'm going to take the top row to use that to solve for x. So x plus 2y plus 2z, that's also equal to 0. And so if I solve for x here, it's just going to be -2 times y, which was -1/2 of t, minus 2 times z, which is t. So it's just negative 2y minus 2z. I guess I need a little bit of room here. So that becomes negative t. Guys, sorry, I ran out of room. It's negative t there on the far end of my board. Negative t for x. Let's bust out that variable. So I'll bust out that variable for v. If I bust out that t, I have a -1, a -1/2, and a 1. Right. Okay, so just busting out from the x, y, and z here. Those are the expressions I would get. And so what's my first solution? Let's just put it right here, guys, since I have a little bit of room. It's e to the lambda t. That would be e to the negative t times the vector -1, -1/2, and 1. Just like that. So let you guys catch up for a second while I erase over here a little bit. Okay. So that's the first step of the process here. Now I have to try to figure out my second and third solutions coming from those other lambdas. So let's just come over here so we have enough room, and let's just take the lambda. What was the other lambda? 1 plus 2i. That was given to us originally. Right, so that's just the first lambda from the hint. So the hint gives us this lambda here, and what I'm going to try to do now, guys, is do the null space for this. Now watch this one. This one's it's going to look horrible when I first write it down, but then I am going to be a magician and simplify it really nicely. Okay, so I'm going to subtract 1 plus 2i from the diagonal of A, from the main diagonal of A. Subtract 1 plus 2i from the main diagonal of A. So I have -1, and I'm subtracting 1 plus 2i. Let's do that very carefully. It's -2 minus 2i. And then the rest of the first row is just -4 and -2 again. Now I'm going to go to the second row. I have a -4 in the first slot. And then I have to take -5 and subtract 1 plus 2i. That's -6 minus 2i. And then I have a -6 on the far right slot. And finally, the bottom row, I have a 4, I have an 8. And then in the bottom right corner, I had a 7, but I have to subtract 1 plus 2i. So that's going to cut it down to 6 minus 2i. There's your matrix. That look like fun?
Yeah.
To do the null space here? I'm going to do it without breaking a sweat. Watch this, okay? First thing is, I know I get to cross off a row. I'm actually going to cross off the first row, mainly because I see a potential to combine this -4 with a 4 and make a 0. If I cross off the second or third row, I would lose that opportunity to combine the 4 with the -4. So it's not that this is the only right answer, but I just think it'll be easier to just get rid of the first row. I don't like seeing this I thing in the upper left corner right away as the first thing in the matrix, okay? And so if I imagine for a second that I had been doing an ERO, that crossed off row is really reflected in a row of zeros at the bottom, right? That where I drew that line through, that's really what that means. Let's take the bottom row and move it up to the top. Okay. You guys remember back in February when I was really picky? It's like, oh, you're going to permute 2 rows. You got to write that down, P13 or whatever. Now we're getting really, we're confident enough we can just do this kind of flailing our arms around, right? Okay, just move the bottom row to the top. And then I'll leave the second row exactly where it is. Okay, now I want to add the first row to the second row. Okay, so I'm going to leave the first row the same, 4, 8, and 6 minus 2i. And I'm going to add the first row to the second row. That'll give me a 0, and then a 2 minus 2i, and then a minus 2i, right? And then the rest of the matrix is all zeros on the bottom. Okay? So this is how this is going to look. Now, you could see, okay, so here's where I just want to make a comment here. You really don't want to divide by complex numbers if you can help it. You really don't want to do that. So don't write this down for a second, guys. Don't write this down. Just watch this thing. If I label my unknowns like I usually do, and I say, okay, z is free. Now I want to solve for y. Well, take a look. For y, if I go to that middle row, I would have 2 minus 2i times y minus 2i z, which is t, equals 0. If I want to solve this for y, I have to actually divide by 2 minus 2i. And you've probably never seen me doing this in this class, taking like a reciprocal of a complex number. You can do that, of course, but it's not that easy to simplify it. Like this is a fraction and it's got a plus in the denominator. I mean, I don't even like thinking about the algebra for that. So you know what we're going to do here, guys, is something a little different. I'm not going to solve it this way. I'm not going to set up a free variable for z and solve it this way. What I'm going to do, my friends, is I'm going to use that A-B trick to avoid having to introduce a free variable. Now, I know what you're going to say. You say, oh, you only do the A-B trick if there's two numbers, if it's an A and a B. And here we have a 3 by 3 matrix. But if you look just in the second row, only on the second row, notice that x has already been multiplied by 0. It's actually not involved at all in the second row. It's really just the y and the z right here. So you know what I'm going to do? I'm going to do that A-B trick just on the y and the z. I'm going to switch the order of these and do a sign change. So the 2i will become a plus, and then the 2 minus 2i below it is switching places with the 2i that we had before. So is everybody with me on this? I'm doing this A-B trick even though it's a 3 by 3 matrix because one of the variables is not in the picture right now. On that second row, the x is not in the picture. So I can play this game with the A and the B where you swap them and do a sign change just on the y and the z. Now, I still have to figure out what x is, but at least so far I'm like 2/3 done. Okay, is everybody with me? That makes some sense? Now, if I want to solve for the x, of course, I need to go to the top row. Let's take a look. 4x plus 8 times y plus 6 minus 2i times z. This is the top row. It should be 0. If we're doing a null space, it's going to be 0 for sure. And let's go ahead and plug in what we already wrote down for y. Y is 2i. And then on the z term, I have 6 minus 2i times z, which is 2 minus 2i. All of that adding up again to 0. Okay, let's keep going. 4x plus 16i, and then plus, I'm going to FOIL this out, guys, 12 minus 12i minus 4i, and then plus 2i times 2i, which is actually minus 4, is still equal to 0. Still equal to 0. If I'm going too fast, I'm basically just playing with complex numbers here. It's not terribly exciting Math 250B material, but it's a necessary part to solve for the x. I'm trying to fill in this spot right here. What is x? Okay, well, if you look at what we have here when we kind of work all of that out, I'm going to try to solve for x, but before I do that, I realize that a bunch of stuff is simplifying. The 16i, the 12i, the 4i, those are all canceling. And I have 4x here, and what else is left? Oh, just plus 12 minus 4, which is 8, is equaling to 0. And so sure enough, we can immediately get x equal -2. Yeah. So I'm going to put that one right here, -2. That took a little bit of work to get that vector. This is the reason I wanted to do this problem, guys. Part of the reason was to just show you how to work with these 3x3 matrices that have imaginary numbers in them. People get intimidated by a matrix that looks like this. Actually, once you cross off a row, introduce a 0, and get this thing at least partially row reduced. This is not a full row reduction. Partially row reduced enough to use this A-B trick is actually not so crazy. Not so bad. Okay. Are you with me? Brandon?
So can you do that A/B trick, but on like, if they wasn't in complex numbers and you got it?
Mhm. Yeah. In fact, there was a problem earlier today. I could have done it right here. I could have done it on the Y and the Z right here. I could have said, oh, I'm gonna do a -1, a 1/2, and a 1 like that. And then use the first equation to solve, well, in fact, you see, we already got the Y and the Z, and then we can solve for the X. Yeah, you can do that. The other thing you can do is if it happens to be, what if you had whatever, and then you had, I don't know, let me just make up some numbers here, a 4, and then a 0, and a -6. You can do the A/B trick on XZ, the X and the Z. So here I'm doing it on the Y and the Z, but you can do it on X and Z or X and Y. You can actually do it with any two numbers. It requires you just to have 1 0 in that row of a 3x3 matrix. Yeah, that's a really neat idea. Yeah.
So for this, it would be 6 0 or 6
Six,
and then
Something and 4, right? And then I'd have to fill this in by using some other row. Yeah, that's exactly right. Isn't that clever?
That is great.
It works. It works. Yeah. I probably should have mentioned this sooner, but we've used it many times on the 2x2 systems. It's just we haven't appreciated that a 3x3, really oftentimes there's a 2x2 within it that you can play this game with. Yeah.
The only requirement is 0.
There must be 1 0. Yeah, if this was like a 1 or something, yeah, then you're out of luck. Then you're out of luck. Okay. Other questions about that little trick? You don't have to use it. You really don't have to. You can still set up a free variable, back substitute, do the Gaussian elimination the way we've been doing since February. Nothing wrong with that. But this is just a little bit of a time saver. Okay, so I've got my eigenvalue and my eigenvector. Now, the nice thing about having complex numbers here, guys, is that we don't have to look at the other eigenvalue. I don't have to think about 1 minus 2i. That I was calling lambda 2 over there. I don't have to do that lambda 2. So all I have to do now, guys, is build my solution. I'm going to denote this as x2, 3 of t. Because we have x1 of t is over there. That's the first one. Now, what I'm going to do here is produce the second and the third one. I take e to the power of 1 plus 2i times t, and then times this eigenvector that we just wrote down, which is -2, 2i, and 2 minus 2i. Okay. By the way, somebody in my session yesterday asked me if it's okay to just divide through by 2 on everything in this vector. The answer is yes. It's just a scalar multiple of that vector, but I'll just leave it the way I found it. And that's totally okay. Now, what I have to do here, guys, e to the 1 times t, so that's e to the t, and then e to the 2it becomes cosine of 2t plus I times the sine of 2t. And then I do need more room, it looks like. And then I have to multiply that by the vector that I get when I bust this thing apart. So -2, 0, and 2 for the real, yeah, that's right. The real part of my 3 slots is a -2 upstairs. There's no real part in the middle, and there's a 2 downstairs. And then plus I times, well, I look for my I in my vector. There is no I on the top slot. If I look in the middle, I have 2 factors of I. And if I look on the bottom, I have -2 factors of I. So it's going to look like that. Okay, so there you go. You have written down the normal thing, guys. All that is just the usual thing here, guys. is one of the most important things in chapter 9. The solutions are built out of those eigenpairs, e to the lambda t times v. It's all I've done so far. Now, what do I have to do next? Yes, you remember, it's the Floyd process, which we learned in section 9.4. So let's just review that. I'll go kind of quickly here. I think people are mostly pretty comfortable with it, but let's just write it out for the Floyd part. I keep the e to the t totally outside. And then I do like the first and the last. The first part would be a cosine of 2t times the vector -2, 0, 2. And then the last part, I have I times I, which is actually -1 times the sine of 2t times 0, 2, -2. Go ahead and write it like that. So in terms of Floyd, if you're keeping track of the Floyd, this is the F and the L part of the Floyd. And then we have to do the outers and inners. So the outer is the O and the inners will be the I part. And what is the outer term? Well, I'm going to have the cosine, right, of 2t times this vector with the I on it. That's 0, 2, -2. Okay. And then the inner term, I've already factored the I out of it. The inner term has sine of 2t being multiplied by this real vector here, -2, 0, and 2. Right. So there you have the outer and inner term of the Floyd. Now, I mentioned in class, okay, this is still not the final answer because you still have an I, one last I that's just still in the expression. We have to get rid of that. And the way you do that is the F and the L part by itself will make up our x2 solution. And then the outer and inner term by itself will make up the x3 solution. So let's actually write them down. I know it's a little bit of writing, but it's always helpful to kind of get an idea what these things are going to look like. So the x2 of t is just e to the t times the FL part. So cosine of 2t times the vector -2, 0, 2 minus the sine of 2t times the vector 0, 2 and -2. Okay, there's your x2 of t. And then your x3 of t. So this one is coming from the first and the last part, the F and the L. And then the x3 of t is going to come from the outer and inner part. And that's just this last part. Don't forget, though, that the e to the t is part of that. So you do need to keep this e to the t into both solutions. But then I have a cosine of 2t, right, times 0 to -2 plus sine of 2t times -2, 0, and 2. Right, just like that. Probably not a bad idea. Put a box here. Somebody in my review yesterday asked me, well, why can I just do that? Why can I take the whole Floyd thing and just chop it up and do the FL part as if it's alone and do the outer inner part as if it's alone into two separate terms, and just the I magically vanished from what we have. There's no more I here. So they asked me, why can I just do that? Well, that's a whole derivation that, is kind of just a tedious calculation. The way it really would have worked out is if we had used the other lambda, we could have generated a whole nother Floyd expression that we could combine with this one in a clever way to get the F and L part by itself and the O and the I part by itself. I never went through that with you. It's just not very interesting. It's a messy calculation that nobody's going to care about. So we're just going to take that as a given, that you can split this whole Floyd thing into the FL piece of it and the OI piece of it. Two solutions as such. And then the final answer then, guys, the general solution, which is ultimately the final thing you would want to have, is just x of t equals c1 times x1 of t plus c2 times x2 of t plus c3 times x3 of t. And I don't need you to recopy x1, x2, and x3 again. You can just go shorthand like that and it's going to be 100% good. Yeah. Okay. Yes, that's a good one. Questions on that? Yeah, go ahead.
Just go over one more time why you crossed off the row one out of them.
So again, I actually could have crossed off any of them. I chose row one just because I don't like starting with an imaginary number in the upper left corner. It's kind of just a picky little thing. And I also saw the potential to combine -4 with 4 and make it 0. If I crossed off the second or third row, I would have lost that and I wouldn't have been able to make this 0 here. Sorry, this 0 here so easily. Yeah, so it's kind of nice to be able to do that. Yeah, please.
For the, calculating part, is there any way I can double check on myself?
This part here.
Yeah, that's what I'm missing.
It's hard to just like be able to figure out if that's just the right number or not. Honestly, if you had the wrong number here, you know, and so you put it there and then it goes through the whole problem here, it's not the end of the world. Like I would say, okay, this student knows what they're doing. They just copied a number. They just have solved that little algebra slightly wrong. That's not going to ruin your day. That's a minor thing. There really isn't a good way to check it unless you really want to take this whole vector and see if it's truly an eigenvector. To see if this is truly an eigenvector, by the way, guys, I'm going to talk about this. Would you know how to do that? If you come up with your eigenvector and you want to check if it was right or not, how could you do it?
You multiply the eigenvector with the eigenvalue to get the A times X.
Yeah, it's this equation. Actually, this is what
Oh, there you go.
this is the next thing we're going to talk about, actually. The AV equals the lambda V. So we could do that if we were unsure if this was correct. I don't want to do the one with all the I's in it. Let's make a nice one here. If I wanted to check if this was correct, how could I do it? I could take this vector and lay it right next to A here. So that would be -1, -1/2, and 1. And I could multiply that out. Because this is AV equals, let's just do it. 1 plus 2 minus 2 is 1. 4 plus 5/2 minus 6. Oh God. I think 4 plus 5/2 would be 8/2. No. 13/2 minus 6, which is 12/2. That would just be 1/2. Okay. Take my word for it. The bottom row is -4 minus 4 plus 7. So -4 minus 4 plus 7 adds up to -1. Look what we got. Look what we got here compared to what we had for the vector that we were working with. Notice that it is just -1 times the original vector. That is compatible with the fact that our lambda is -1 right now. So if I take my vector and I multiply it by the matrix, it should become negative of that vector again. That's right. Seem okay? Yeah, okay. Anyway, I think it's enough. I've done a lot on chapter 9, which is great. I want to do a few more theoretical type questions though, conceptual things that sometimes people feel they need to practice a little bit more. So I've got just the ticket for that. We still have some things to go over. I have not gone over anything about the kernel and the range and the general rank nullity theorem. And I haven't talked about annihilators and variation of parameters and all of that either. So I'm going to try to move on a little bit. Let's go to number 1 on the review sheet. I'm going to tweak number 1 just a little bit to make it a little bit easier. So number one, this is off of the review session. Suppose that A, which is n by n, satisfies a squared plus 6a minus 7I equals 0. So this is I sub n is the identity matrix, and then the 0 matrix is all zeros, right? So then here's what I would like to do. If lambda is an eigenvalue of A, show that lambda squared plus 6 lambda minus 7 is also going to add up to 0. So this is a proof. This is like a conceptual question that involves eigenvalues, obviously. Actually, there's nothing special about the exact equation here. I could change the 6 and the 7 to any other numbers. The same property is still gonna be true. It's still gonna work out. So it's just the fact that whatever equation your matrix satisfies, the eigenvalues of the matrix will satisfy the exact same equation. So you can just literally take your matrix out and put your eigenvalue in, and you get an equation that's true. It's a very famous thing. It's actually quite a famous result. Okay. So I guess to do this proof, this is theoretical, it's conceptual. We want to write down anything that's relevant could be worth partial credit. If you start writing down a bunch of stuff that's not relevant, I won't give you any points for it. It might be correct. If you tell me, oh, if the lambda, you start your solution, oh, if lambda equals 5I, the phase portrait is a circle. Well, that's correct, but it has nothing to do with this problem. Okay, so don't do that. But if you're writing down something that's relevant, I will give you credit for it. Can anybody think of anything that would be relevant here that we might want to write down? Oscar.
If you take the determinant, it cannot equal 0. Can that be one?
Sure. So the determinant of, I'm going to put that over here. The determinant of A minus lambda I should be, well, actually, for an eigenvalue, the determinant should be equal to 0, just to be totally clear about that. That's the characteristic equation. We're going to do this problem without even touching determinants, though. So I'm kind of having it on the side, but that is definitely a good thing to be aware of. Is there's another fact that might be even more helpful here, Lizzie? Exactly, the one that we just wrote down a minute ago, kind of get foreshadowed a little bit. I would probably start out by saying, we know that A times V equals lambda times V. If you just write that down and you don't write down anything else, that's it. You're already going to probably get, let's say this is worth, I don't know, let's say it's worth 5 points. It's a 5 point problem. I'll probably give you 2 points just for writing that down with nothing else. So this is really important. We should make the little additional claim or the additional comment here that the vector V should not be the 0 vector. Okay, so it's always good to try to write down everything that you do know that is relevant. Don't just punt the complete problem away. If you don't have anything written down, I can't give you anything. I want to give you guys points, right? That's my goal. I get happy when I'm giving points out. So write down all the stuff that you know. Okay, so AV equals lambda V. Anybody have an idea where we could go from there? Aaron?
Substitute in lambda for A, but I think that's too far.
Well, so we have to be a little careful. I'm going to remind, I know I mentioned this before. You can't literally cancel the V because then it looks like you're saying the matrix is equal to the number. It does kind of look like that's what's going to happen here, but we need to show how that happens. Like it needs to be mathematically correct how that happens. Yeah, Brian?
You just solve for lambda.
Solve for lambda here? Or you mean like solve this equation? I'm gonna make this equation. This one's maybe not so bad, but I could make the lambda equation really horrible, right? So it might not even be possible to do that.
can we possibly multiply the inverse of the matrix on both sides of that equation to isolate the V on one side?
Do we know that the matrix has an inverse? It's always my first question is if the matrix is invertible, then I can use the inverse of the matrix. But I actually don't know that this matrix is invertible, so I'm kind of out of luck on that part. Yeah, this is a little bit of a tricky step. But what you want to do right now, guys, is take the given equation. You want to take this given equation and apply it on both sides with V. So in other words, what I can say is that a squared plus 6a minus 7 times the identity of V is equal to the zero matrix of V. This is the key step. This is the key step, is that if the matrices are the same, then when I multiply them onto V, I get the same result. Right? So this is a key step. What do I get, by the way, when I take a full matrix of zeros and multiply it by anything? I get the zero vector here. This will be the zero vector on the right side. And what about on the left side? I think on the left side, can't we just distribute it? This is just going to be, a squared V plus 6ab minus 7 identity V. Okay, so I can just break it, basically distribute the V term by term. Something like that, yeah? The right-hand side is 0. I see that part. That's the easy side. On the left, I have to work a little bit. Now, what is the identity times V? It's just V. Because if you remember, the identity matrix is like multiplying by 1. So if I see an identity matrix, I can pretty much just get rid of it. So this last term here is really just 7V. The identity matrix can be just dropped from that. Let's go to the left here. What is 6AV going to be replaced with? 6 lambda V, exactly. So let's do that next, 6 lambda V. And then what about A squared V? That is lambda squared V, actually. By the way, if anybody was wondering about that, can I write over here? If I wanted to do A squared V, the way you would calculate this is you would just do A times V, right? And the AV that you see there on the right becomes a lambda V. Then lambda is just a number. You can flip it to the front. And then another AV shows up and you get lambda V. And so it becomes lambda squared V. It's exactly what we put in right there. Isn't that clever? So A squared V is just lambda squared V. If I had A cubed V, it would be lambda cubed V. But there is one thing that I am going to pull out my red pen for. I'm going to pull it out tonight in hopes I don't have to pull it out in a couple of days from now. Because this is the thing people sometimes write down that is definitely not good. Which is I see people do stuff like this, A and V, and they want to like square it. That might look good at first. It's like, okay, yeah, that's kind of what I need. I need A squared to show up. So they want to square this thing. But to be honest with you, what I wrote in the red writing here is actually something that is a nonsense statement. It doesn't make sense because this is a vector. And how can you square a vector? We've never done that, right? We've never said, let's take a vector times itself. The closest thing we ever did to that was maybe taking an inner product of a vector with itself. That's a whole nother topic. That's chapter 5. We're not even going to deal with that for this exam. And so we're not talking about inner products here. This just doesn't make sense. So be a little careful. If I see even just this, my red pen comes out really fast. That's just a statement that just does not make sense. So we have to stay away from squaring a vector, right? But if we have a squared times v, that's a whole much better matter. We can just work with it like I showed over here. Yeah. Okay. So where am I at now? I'm here on this bottom line, and what can I do with that? Because I'm trying to still finish my problem here. Yeah, there's a v in all three terms, so I'm gonna factor that out. So let's get this red writing out of here before anybody decides to get excited about it. Right, so what we're gonna do is on the left side, let's just factor that v out. That'll give me lambda squared minus 6 lambda, I'm sorry, plus 6 lambda, and then minus 7, right? And then the right-hand side is still equals to 0, right? So this is what we have when we factor the vector v out of it. And let's remember, guys, that the v was not 0. So what do we have? We have a vector that's not 0. We are scalar multiplying it by some number, and it's becoming 0 when we do that. What's that tell you about the scalar that you were using? It has to be 0, which is exactly what it says to show. Show that that is 0. So I'll just say since v is not 0, we conclude that lambda squared plus 6 lambda minus 7, that one is 0. That one is going to be 0. So there is how you can make that argument work at that point. Okay. Does that seem all right, guys? It's a pretty nice one. Definitely worth reviewing. If you want to practice that a little bit more on your own, all I would recommend is, just change the numbers up here and create your own problem. It all works the same. There's nothing about the 6 or the 7 that has any real impact on this problem. You can change those numbers all day long. Okay. So far, so good. Let's do, before it gets too late, I want to do a couple of things on linear transformations, the kernel and the range and that topic. So the first thing is, I'm gonna do one that's computational, and then I'm gonna do one that's theoretical. So I'm gonna do one of both, kind of back to back right now, as long as we're okay. I feel actually pretty good about chapters 7 and 9. I really covered them with all these examples. We've hit a lot of the topics. I just think we need to spend a little time on chapters 6 and 8. So let me give you something from chapter 6. This is actually problem number 9 on this review sheet. And it just says, consider the linear transformation and I'm going to call it T, right? And T is going to go from the M2 of R going over to the P2 of R via, okay, so we're creating T. T was our notation. This is in chapter 6. This is actually from before spring break. So this is the chapter that probably needs a little bit of refreshing. I'm going to take a 2x2 matrix. I'll write it as A, B, and then C, D. And I'm going to spit out as an output a quadratic polynomial. That's the P2 of R. So I've made up a formula here. A minus B plus D, and then plus negative A plus B minus D quantity times x squared. Okay, and I'm going to ask the following question. Find a basis for the kernel of T and the range of T, and decide if T is 1-to-1 onto both or neither. Okay, so it's a good question to cover a lot of ground on this topic. It takes us back to chapter 6. This goes back actually before spring break. That's when we did this one. Anybody remember any of this stuff? You do?
Yeah.
Oh, good. Good. Okay, well, maybe this won't be too bad. Let's try it. Okay, let's just put you to the test here then. Do you remember what does 1-to-1 mean?
Means kernel equals 0.
Beautiful. Kernel of t equals 0. Exactly.
Can we conclude that it's not equal to 0 because there's no c that comes up to the right side?
Yes, I'll say something about that in just a second. Before I do that, can somebody remind me what the onto means?
The range.
The range is the dimension of the range.
Who wants it? Huh? Yeah, the dimensions are equal, but we can actually we don't even have to mention the dimension. You can just say range of t equals W. And by the way, so just so we're clear, the V is always the input, the W is always on the outputs, right? So in this example, I have an input, the matrix, the output, the polynomial. Yeah, Oscar?
I was gonna say, does the dimension of the range have to be greater than the dimension of V for it to be onto?
Not necessarily, no. Remember, the range is a subspace of W, which means it's not really being compared with V. The range is over here on the W side of the equation. Yeah, exactly. But there are a couple of facts that are worth knowing. And this gets to what Brandon was saying a couple of minutes ago. The first one is that if V is bigger than W. Okay, so this is something we do need to kind of memorize. Unfortunately, I try not to have too much to memorize, but there's a little bit. If V is bigger than W, then T cannot be 1-to-1. Okay, so actually that is what we have here. So we have to remember the dimensions. So there's a lot here. There's a 4-dimensional vector space V. P2 of R is, if you remember, is 3-dimensional. So we actually have to remember this stuff. The thing that's nice about this, guys, is that if you're studying for this midterm tonight, you're also studying for the final next week. Because questions like that have to do with, chapter 4, knowing the dimensions of these vector spaces. So it does rely on that earlier material just a little bit. The second fact is just to turn this the other way around. If the dimension of V is less than the dimension of W, and this is already in your notes, I'm just trying to tell you that this is something important to review. In this case, T cannot be onto. Right. And then the third outcome is if V and W have the same dimension, then remember what we have for a conclusion here? Both. Both or neither. Exactly. So T is both or it's neither. And that's exactly how the question is being phrased here. Just a quick tip on this. There will almost certainly be a question like this tomorrow. If you notice, oh, V is bigger than W, so so T can't be 1-to-1. So you come over here and you cross off 1-to-1, and of course that means you're also crossing off both. A lot of people will just do that. That's all the work they show. So I get their paper, I'm looking at it, and all I see on the paper is that they just cross these two words off. There's no mention of any facts. There's no talking about even writing down the dimensions. And so, guys, that really is, you're tempting me to get that red pen out again, right? Don't do that. Like, explain this one. So you could cross it off and then just say something. Even if you wrote V bigger than W, technically you shouldn't write it like that. You should write dimension of V bigger than the dimension of it. But even if you wrote that, I would be like, yes, I know that they know what they're talking about, rather than just, oh, they kind of crossed a couple of things off, like it's almost like it's a stray mark or something. And I'm like, okay, do they really know what they're talking about here? So don't leave it up to doubt for me, because you don't have to spend a lot of time. This takes like 2 seconds to just give me a quick little reason. Okay, so that's something that I think a lot of us could be better at. I know when I was a student, I could have been better at it too. I didn't always do the best job when I was first learning this stuff, but it's an easy way to make sure that your professor's red pen stays away from your paper, is give me a little explanation there. Okay, So we already know that this transformation is not 1-to-1. Onto is still up in the air, and we'll get to that when we work on the range, okay? So the question is asking us to find the kernel and the range here. It doesn't matter which one you start with in this case, I don't really care. We could just start with the kernel. Oh, is there any other really important thing that I didn't put on the board yet that has to do with kernel and range?
Oh, the nodally range theory.
Yes, yes, thank you for remembering that. That's exactly right. The other big fact that we always seem to be coming back to is that the dimension of the kernel, right, plus the dimension of the range equals the dimension of V. Okay, so I am hearing a lot of good stuff out there. That's exactly the general rank nullity here. Exactly. And so like on this problem, we already know that the dimension of V is 4. And so it's just a matter of rounding up the rest of these numbers. Okay, let's work on the kernel first. So I'll do that over here, the kernel of T. Remember that, so some folks last night weren't even quite remembering what this is. The kernel of T, this is the set of vectors V in capital V that get transformed to 0. So it's the set of vectors such that T of V is equal to 0. So what you want to do if you're trying to find the kernel is you just want to basically write that down. T of A, B, C, D is equal to 0. Now, just to be clear, this is not the number 0. On the right-hand side, this is not the number 0. This is the vector 0. And so if I look at what my W is, it should be like quadratic polynomials that have like this form. Instead of just writing 0 here, it might even be helpful to kind of just put it in the form of what these outputs are looking like. So it's 0 plus 0x squared. That'll be maybe helpful because then when you actually plug in what the formula is on the left side, so if I just evaluate on the left side what the T of A, B, C, D is going to give me, it's easy then to match it up with the right side. This goes with this goes with that, right? So you can just see that one directly there. And so you create equations here for each of the different types of terms. The constant term, right, have to match up, and then the x squared terms also has to match up. So we'll get for the constant term, a minus b plus d, okay, that should equal to 0. And then the x squared term on the left side, negative a plus b minus d, on the right side, also equal to 0. Okay, and then I can put that all into a matrix. Now, here's the trick though, guys, be careful. There is a silent c vector, a variable here. It's just not showing up in the equation right now. But leave a space for it. Leave a space for the c here, because even though it's not showing up in any of the equations, it is part of the notation of these polynomials. So we get the second equation looking like this here. Okay, so that's what we would have, is a little matrix system like that. Now, usual thing with this system of equations is we want to hit it with EROs, get it into row echelon form. And you can actually see that the second row is literally just the negative of the first row. So you can wipe it out by just adding that first row to the second row. It just wipes it out completely. And I have a pivot. I have a pivot right here in the first slot, and that is the A variable. Notice that my unknowns are going to go from A to B to C to D, just like that. Okay, I need a little bit more room, it looks like. Come back over here. Is everybody with me so far? Kim?
And then the BCD will become free variable.
That's the next thing. Yep, that's exactly the next thing. I'm going to write it down. Thank you. Yes, so B, C, and D are free variables. I'll do what I did last night, which is I'm just going to change them to R, S, T. I just like to be in the habit of switching to those letters when I have free variables. You don't have to do that. If you just want to continue to call things B, C, and D, I don't mind. But I like to do this. It just kind of gets me into the habit of it. And then I have to solve for A. And if you look at what A is, A would be equal to B minus D, right? Is that right? A is equal to B minus D, but in this notation, it would be R minus T. Okay. So this is my relationship of my variables from the matrix that would give me the kernel of T. So then I'm going to see if I can write down the kernel. Something like this. Here's A, B, C, D, and such that R, S, and T is in the real numbers. Thing like that. What do you guys think so far? Everybody happy with that? Oscar.
From there, you just take out the variables, right? You have 3 separate vectors.
Yeah, I think we're gonna get 3 variables there, which means I'm already kind of foreshadowing this number is probably going to be a 3. So as I'm thinking about filling out my general rank nullity theorem, I'm getting in pretty good shape here, right? But before I do that, let's come back to this for a second. Is everybody happy with this? Why not? I have to, but I'm not done yet. I agree with that, but are you happy with what I have so far? That's my question. I am making a very common mistake on purpose to see if anybody can catch me. There is something wrong with what I wrote down on this blue writing. You know what it is, Brandon?
Would C have to equal to 0?
No, C is actually quite the opposite. C can be any number because it doesn't show up in the equation over here, which means it's completely free. So it's actually okay. Yeah.
Would you have to include the R minus T in the basis? Or like the...
Oh, I haven't gone to the basis yet. The basis is when I'm gonna bust out the variables. So far I just put the A variable there. But my red pen would come out on this. What is wrong with that? Let's see, the kernel, do you think you know, Brian?
So R minus for RT equal T.
Actually, there's nothing wrong with the variables. The R, S, T, R minus T, this is all correct here. Okay.
Yeah.
Getting closer, getting closer. The kernel of T is a subspace of what? Of V. What is V?
So we have to put in.
It should look like something from V, right? It should look like a 2x2 matrix, right? I did not do that here. What I really should have, guys, this is really important. Make sure your vector looks like a 2x2 matrix. R minus T, R, S, T. Now I'm happy. Now I'm happy. So it's very easy to just say, oh, I'll just draw them out as a bunch of slots. But it needs to be actually expressed in the right notation. Okay, but once we get that down, then getting the basis for the kernel, you guys have already kind of given me the roadmap for doing that. For the basis for the kernel, I just have to bust out my variables. So I bust out the R, I'm going to get something like a 1, and a 0, and a 0. And then when I bust out the S, I'll get a 0, and a 0, and a 1, and a 0. And then when I bust out the T, I'll get a -1 and a 0 and a 0 and a 1. And there you go. There you go. There's your basis for the kernel of T. All right. So 3-dimensional kernel with that basis as such. Okay, so we're done with the kernel part. Everybody good with that? Yeah.
And our basis is supposed to look like that, right?
It's just this what I wrote here. Just these are 2x2 matrices listed out.
Oh, okay.
I think I asked for a basis for the kernel of T on the take-home quiz, and there were some people who were leaving the letters in. Okay, the whole thing, when you go to the basis, that's when you bust them out, right? Your actual basis vectors should not have the A, B, C, D, or the R, S, T, whatever they are, those should be busted out completely. Yeah, exactly. Please.
So since we, like earlier, we said range of T is a subspace of W.
It is.
So then when we do range of T, it should also look like the polynomial.
They better look like polynomials. We're gonna get to that. Yeah, we will absolutely want to make sure that our range looks like polynomials. Yes. Okay, so let me give myself some room to look at the range. It's really nice, guys. We can actually review this whole chapter just with this one problem. I mean, this problem has everything in it. So I don't have to like sit here and do like 5 examples tonight. We can just kind of do one and then you try the sample test. Keep in mind though that on another problem, maybe the inputs are the polynomials and the outputs are the matrices. Don't let that throw you off, right? The V and the W could be changing roles a little bit. But the idea of the big picture of how you work with these things is always the same. Yeah, so let's talk about the range of T. Actually, sorry, Aiden, go ahead.
So if it was vice versa, W was a
Uh-huh.
matrix, then that would have been fine what we had before.
It still wouldn't have been fine. What I had before, Aiden, what I had before when I wrote this down, what was it? It was RST. When I have this right now, what universe is that living in? 4 slots. What's that vector space? It's just R4, right? If this was a vector in a universe, it would be this vector space, R4. This is still not looking like a polynomial yet. Yeah, so anyway, I mean, if somebody made a mistake and you wrote this as a column, yes, my red pen would come out. It wouldn't ruin your day. I might take off a couple of points. It's not gonna be a huge thing, but it's an easy one to not have to lose those points. Let's not lose the points. Make sure your vectors are looking like vectors from V if it's the kernel. And if it's the range, they should look like vectors from W. By the way, we are in a really good position now because we already know what the dimension of it is supposed to be. So this is helpful when you know ahead of time what kind of dimension you're supposed to have. Let's try the range of T here. Talk a little bit about this one. And again, since it's been at least 5 weeks or so before spring break, let me just remind you how you do the range. The range of T is where you take the span. You take a span of, and then what you do, guys, is you just transform a basis. So I'll call it V1, V2, and ... up to Vn. You just take T of all of those basis vectors and throw them into a span. And this is just a list of vectors that we have to calculate. Now, one thing you have to do is figure out what basis, like what are your vectors here? What is V1, V2, V3? So you're actually looking for a basis for M2 of R. There are millions of correct answers for that. There's lots of right bases, but there's probably one basis that's the most obvious one. It's certainly the one that I've brought up the most often. Does anybody know which basis it is? Brandon?
1, 0, 0, 0, 0, 1, 0, 0. 0, 0, 1, 0.
Right. All the way across, right? You just move that 1 to the 4 different corners of the matrix. This is the easiest basis to use. You don't have to use it. It's called the standard basis for M2 of R. You wouldn't be required to use that basis. You could choose any basis. But keep in mind that you're going to have to plug each of these vectors into the T. And I would rather have my A, B, C, D values be really nice numbers. Right? If you choose a more complicated basis, then you're going to get messier calculations. You don't need to go there, right? Just keep it simple. Just nice, easy vectors. If I want to plug 1, 0, 0, 0 into this formula, the A is 1 and all of the other letters are 0. So if I look at how I'm going to get an output from that, if A is 1 and all of the other letters are 0, then I just have a 1 for a constant term, and then I have a minus on the x squared term, right? So would that just be 1 minus x squared, right? 1 minus x squared. That's the first one. Okay? Now, actually, let me give you a little tip here. We can already stop. Because we already know that the range is one dimensional and I've got my one vector already there. So believe it or not, this is going to be my basis. But just to confirm, let's calculate the rest of these. What is T of 0, 1, 0, 0? If I put a 1 for B and everything else is 0, I'll get -1 and then plus x squared. So that would be -1 plus x squared, right? Okay. What about when I put a 1 for C? Everything else is 0, but 1 for C. Well, then I have nothing here and nothing here. It's literally just 0. Nobody's going to be happy with that vector in a basis. And then the last one, 0, 0, 0, 1. If I put a 1 for D, then I will get 1 minus x squared. Okay. Now, the student who hasn't been paying attention all semester, which is none of you guys, but the student who has not been paying attention all semester would glance at that and say, oh, it's 4-dimensional. 1, 2, 3, 4 things there. But we know better, right? We know that these vectors are only going to be 1-dimensional. And that's because you're only going to spend $1,000 here. You would not buy the same thing twice. You're going to get rid of that one because it's the same as the first one. You're not ever going to buy the 0 vector. That's a cheap, free vector. And this vector is just the negative of this vector, which scalar multiplication would allow me to create. The only one I need to keep is just this first one, and that is going to be the answer. The basis for the range of T would just be 1 minus x squared. Notice, it is a quadratic polynomial. It's exactly the way it should look based on the way the V and the W are set up here. Okay, great. We've got the basis for the kernel. We've got the basis for the range. Is this thing going to be onto then? Just take a look at that question. Let's see. So onto means the range of T equals W. How can I decide that? I've got W here. I've got the range of T here. Are they the same? No. The range is only 1-dimensional. W is 3-dimensional. That if they're not the same dimension, then they're not the same, right? So this is actually not onto either. So this one, the only thing left is it's neither. Yeah.
So we could have figured that out
a while ago. Yeah. Actually, it's kind of ironic. We could figure out whether T is onto by doing the kernel. Even though the definition of onto is talking about range, the minute we did the kernel and we found out that it was 3-dimensional, we actually not only figured out that it was not 1-to-1, but also it's not onto because the range is too small. It's too small. The dimension of the range is only 1, right? So yeah, a lot of times I'll ask this question second. Like I'll ask the first because I want you to figure out the kernel and the range first, and then I'll ask this as a follow-up. But if you're paying attention and you see that I'm doing that, you might be able to get that second question answered first as you start working it out. If you figure out, oh yeah, the dimension of the kernel is this, and so therefore the dimension of the range is that, and oh, it's not matching up with W, oh, so it's not onto, and you just know that already. It's actually not that hard of a question in that case. Yeah, so anyway, the biggest mistake is not putting the vectors in the right form here. That was a big one we got to try to be careful of. But other than that, I think this is hopefully making sense. Oscar, please.
Kind of going back to that matrix there.
Okay, yeah.
From I guess the other sections, we know that the first column is your basis already for range.
It will be, yeah, it will base, but only once I write it as a polynomial.
Yeah, right. I was gonna say, can I use that and multiply that by the polynomial? What's the general form? So it's like ax squared plus bx plus c, and then kind of correspond each a's with a's, b's with b's, and c's with c's. Or is that too much? And it's
I think it's a little. Let me see if I can answer your question a slightly different way, as I'm not quite following it. Let's play dumb for a minute and imagine that we're looking at these four things and we can't tell that they're LD yet. It's just, maybe they're not so nice. You have four different polynomials. If you didn't just look at them and be able to notice that, oh, obviously they're all just multiples of the first one, you still have a game plan. And that game plan is to write these vectors into the this actually goes back to chapter 4. How do you test if a set of vectors is Li? You lay them into the columns of a matrix. This is what we're going to be reviewing again for next week when we get to the final. And this first polynomial, you would write it as a 1 and a 0 and a -1, right? Constant term, x squared term. And then the next vector would be a -1 and a 0 and a 1. And then the third one is literally all 0. And the fourth one is a 1 and a 0 and a -1. And if you're testing for Li, you augment the matrix with all zeros. That's the way that is done. Obviously, this row cancels out. This row cancels out. We circle this pivot. Usual thing. It's just the same matrix, isn't it, as the one over there. And what do we do here? If you remember from chapter 4, any unpivoted columns correspond to the vectors that you're going to get rid of and throw away. And you only keep the pivoted ones, which in this case would just be that first one. Yeah, so is that kind of along the lines of what you were?
Kind of, yeah.
Okay.
I'll elaborate after.
Office hours or something. Okay, that sounds good. Everybody feel okay with this though? Yeah, so if you do get a list of outputs here and you can't tell if they're Li or not, go ahead and throw them into the columns of a matrix and do this ERO process and just keep the pivoted columns as your basis. That's the way that would work. Okay. I think, can I erase this example? We okay with that? I'm going to do a theoretical problem now about this same chapter. This one was computational, the one we just did, but I'd like to do something that's slightly more conceptual. And then we'll see how much longer I might go. I don't know. I'll look at my stuff and see what else I haven't talked about. I know I haven't talked about annihilators and variation of parameters yet. By the way, so before I do anything else, does everybody know the formula for the variation of parameters? I'm totally going off topic here. I just want to get this down before I lose any more people.
U1 is equal to the minus the integral y2 minus times f, sorry.
Okay.
Over the constant.
Beautiful.
And then U2 is
You're on a roll.
Of y1 times f over the constant.
Okay, everybody's gonna know those, right? People always ask me, why don't you give me a cheat sheet so I can just write that down? Well, because I want to give you points for putting it on the test. So please just know those formulas for variation of parameters. I may not do one of these tonight. It's totally plug and chug. It's not terribly conceptual. The only thing about variation of parameters is you have to know when to use it. It's really in a situation, where you have a second order differential equation. So this is variation of parameters. Sorry, I'm getting a little off of my game plan, but that's okay. This is for second order differential equations. And especially if you don't have an annihilator for the capital F that's on the right-hand side of the equation. So it goes without saying, I'm going to give you that table of annihilators. And if you don't know how to annihilate the big F that's in that differential equation, then that might be pointing you towards trying to use this method here. Was that a hand? Yeah.
Yeah, so we, for variation parameters, we're only going to do it with n.
Exactly. We didn't ever learn how to do it for larger values of n. It's not that you can't, it's just that it's too messy to do it on paper, pencil and paper, so I won't ask you for that. Yeah. If you see a problem like this and you get to the integral and you realize, oh my gosh, I don't know how to do that integral. Okay. What do you suppose you're going to do? you're taking the exam, you know you're supposed to use variation of parameters, you start crunching out the calculation, you do y1, you do y2, you write down the complementary function, you write down these formulas, you plug stuff in, you're like, I can't seem to do this integral, it's not working out for me, it's not in my table. What do you suppose would be a good strategy? Yeah, Dave.
Maybe just like leave it within the interval.
Exactly. I would just like let it go. Do not erase it. This is what people do. They say, oh, I must have done it wrong. Let me start over. And they lose 10 minutes, 15 minutes re-erasing. Sorry, swallowed wrong. So they'll end up losing a bunch of time, and probably whatever the mistake is a minor thing. It's probably not something major. You have to know that I'm not going to ask you for a crazy hard integral. We haven't been doing them even in the homework, and that's not what this class is testing you on. So if you get to an integral that you're like, I don't know how to do that integral, I would recommend just leave things as they are. And you know, you can carry out the rest of the work, maybe just stick this thing right there with the integral still there. Stick this one right here, and then just call it good. And if you have time, like at the end of the exam, sure, go back and see, maybe you made a mistake. Take some scratch paper, try it again on the scratch paper, but don't erase a whole bunch of stuff that's probably mostly correct and lose all of that work until you really know what's going on there. Okay, so just some advice for the exam. A lot of times a lot of people know this stuff better than they think they do, but then it doesn't get onto the paper in a way that I can give the best outcome possible. So just wanted to give you that little bit of advice. Okay, having said that, now I want to go back and do one more theoretical problem, and then I might just call it a night. Okay, there are a couple other problems that I did last night, and you can watch yesterday's video if you really want to see some more of these problems. But let's do, this is number 11 on the sheet. And I'm going to go ahead and do this one next. So this one says if T, which is going from V to W, is a 1-to-1 linear transformation, and the vectors v1, v2, v3, that set is Li. So if v1, v2, and v3, if that is Li, then show that the set of T of v1, comma, T of v2, comma, T of v3 is Li. That's right. Okay, give myself some room here. This part off. Yeah, so this is a proof. This will be something conceptual here that we have to try to explain a little bit. Does anybody remember, how do you actually show that a set of vectors is Li? I know that on a practical problem, you would lay those vectors into the columns of a matrix and do EROs to remove any unpivoted columns. But what if it's abstract? Like this is abstract. I don't know how to put this into a matrix because there's no, meat on these vectors that I can like put slots into a matrix or anything like that. Yeah, Kim?
Sorry, I have a question about the variation of parameter.
Oh, okay, yeah.
But the view, it's Wronskian.
Wronskian.
And then
Of y1 and y2. Yeah, that's right.
I think well, involved the
Yes. Yeah.
Yeah.
Yeah, that's the equation for that, right? How do I show that a set of vectors is Li? That's if there's two. If there's only two vectors, you can argue it by just saying, yep, these are not scalar multiples, so they're Li. But if I have a whole list of vectors, in this case I have, I guess just 3, how would I do that in general? Yeah.
I think there's like a list of characteristics, but it has to, the matrix, or if you put it into a matrix, which I guess you can right now, has to be invertible. The kernel has to equal 0. So,
Yeah, if we had a matrix, all of that stuff would make a lot of good sense. Absolutely true. This is really gonna force us to remember the definition of Li, which is like the actual conceptual definition of it is something that we don't use as much. So it's why this problem is a little bit harder to think about. But what it is, so I'll get you started on this. Is you need to show that the only way to cancel out your vectors in a linear combination is with scalars that are all zero. So the way I would write it is to assume that C of C1 times T of V1 plus C2 times T of V2 plus C3 times T of V3 is equal to 0. Does this look familiar at all? You know, I probably wouldn't put this on the exam just because it is so abstract and involves linear independence, except that this was actually a homework problem. And I actually did this one. But it's been a while. It's been since around spring break. So it may not be something you remember exactly, but we did actually do this problem. What are we going to need to show here about this expression now?
that C1 to 3 is equal to 0. The 0 vector?
The zeros, they're all scalars. They're all zero scalars. So let's just put that on the side. So we will show that C1 and C2 and C3, that they are all equal to 0. We're going to show that. Yeah, that's going to be the goal. That's going to be the goal. Okay. Looking at this first line, does anybody have a knee-jerk reaction? What you're going to do with that? So abstract. Most of the time we say, put it in a matrix. I wouldn't even know how to do that. T is
Can you do like C1 times T and then do like C1 times V1 plus kind of like, I guess, like separated?
so I would argue that it's already separated.
Oh, okay.
Like I've already got the terms all busted apart.
Yeah.
So what can I do kind of thinking the other
Nice.
direction?
Put everything
Put
together.
it back together. And that's because T respects addition and scalar multiplication. It's a linear transformation. So T will respect those operations. So guys, what I can do is I can kind of put the T outside of the whole thing and put all of the rest of the terms inside. So I can put the C1 times V1 plus C2 times V2 plus C3 times V3. I can put all of that on the inside. Yeah, so that's just, let's just put a reason over here so we can understand that. This is since T is linear. Since T is linear, we can do that one. Okay? So far, so good. Now, what we have here now, guys, is we have a vector that is being transformed into 0. What does that tell you?
That the constants or like the scalar values have to be 0.
That's where we're trying to get to.
Oh.
Let's not jump too fast. We're going to show that all of those constants are 0. But before we get there, what do you think? If I have T of whatever equaling to 0, what does it tell you about that thing?
It's 0.
Too fast. I know that's where you want to go. But what's the definition? So if a vector gets transformed to 0, what do you know about that vector? In terms of where does it live? Who said that? Kernel? It's in the kernel. It's in the kernel. The kernel of T is those vectors that get transformed to 0. So guys, if I have a vector here that's getting transformed to 0, then that vector is in my kernel. Let's write that down. So thus C1 times V1 plus C2 times V2 plus C3 times V3 is in the kernel of T. That's exactly right. It's basically from the definition of the kernel. That's what the kernel means. Yes, that is what the kernel means. So we would be able to say that. Okay, so we've got that down. But what is the kernel of T for this example? It is what? The kernel is 0 because?
It's linearly independent.
No. Why is the kernel 0?
Because it's it's a one-to-one.
That's the word, right? What does 1-to-1 mean? 1-to-1 means the kernel is 0. So guys, this is just equal to, the kernel of T is just equal to 0. This is since T is 1-to-1. So now we're using the fact that it is 1-to-1. Okay, so in other words, if I find something in the kernel, whatever that is must be 0. Okay, so thus, right, when I have one more line, C1 times V1 plus C2 times V2 plus C3 times V3. If it's in the kernel, guys, it is 0. It is equal to 0. That is the only possibility. Almost done. We've used the fact that T is 1-to-1. We've used the fact that T is linear. What is the one last step we need to make here? Notice that the T is now gone. There is no mention of the T anywhere here. All we have now are just the original vectors, the V1, V2, and V3. What can we do with those?
Now, can we see that C1, C2, and C3 is equal to 0?
They are. Why?
Because you need that C to equal to 0. So when you multiply by the vector, it should be equal to 0.
Too technical, too detailed. Just pick something out of this question that we can just use as a quick reason. Why are those constants all 0? Anyway.
Because since none of the, or since the vectors are Li, none of them could be 0.
The original vectors are Li, right? If the original vectors are Li and they cancel out somehow, then remember what that means. It means they must cancel out in the trivial way. There's only one way to cancel out V1, V2, and V3, which is for those constants to be 0. That's it. So let's just add that. Since V1, V2, V3 is Li, then we know this is just kind of, it is going back a ways, guys. I totally get it. It's going back to chapter 4 where we define what linear independence means. So all of those constants are 0. They're all 0. Yeah, that's a bit of an abstract example, but it's a nice one. It reviews a lot of good stuff about linear transformations. What it means for T to be linear, what it means for T to be 1-to-1, and step by step, I think each step by itself is really not too bad. Yeah. Okay, what I'm gonna do right now, is there any questions on this before I go on? I'm going to probably stop, but before I stop, I just want to let you know where I am on terms of what I covered. So in this review session handout, in case you want to follow up, right? In this review session handout, there are 11 questions here. So I'd like to explain which ones I've done and kind of maybe which ones maybe would be worth looking at if you still had some time. We did number 1. Number 2, we did not do, but I would probably skip it. It's another, it's a very abstract problem about eigenvalues and eigenvectors. If you really run out of other things to do, you could look at it, but I would say it's not critical to do that. We did number 3, we did number 4, we did number 5. We did not do number 6 or number 7. I'm going to write skip next to that as well. That one is probably not anything you need to worry too much about. We did not do number 8. We did number 9. Number 10 is like number 9, and everybody seemed to be doing pretty good with number 9, but if you want to practice kernel and range one more time, number 10 is like number 9, we didn't do it, and then we just did number 11 right now. So the ones that I would recommend, and I did do these last night, I would recommend number 8 if you would like to, and so you can either, how can you do this for yourself? Because I don't really want to keep everybody here. If you want to do number 8, you can either just read the solution in the canvas, because I have the answers to all of these typed out nicely. So you could do that, or if that doesn't work out so good, you can also pull up last night's video, and you will have to scroll through a little bit, but I did these kind of in the same order that I did tonight, and number 8 would be towards the end. As far as number 6 goes, number 6 has a lot of parts. And I would not recommend doing all of these parts because it's just too much practicing of the same thing. I would probably, if you were going to focus on anything, you might look at parts A and C. Those are the 2 parts that I did last night. One of them, part A, is an annihilators problem. And part C is a variation of parameters problem. And by the way, number 8 here, this was a Wronskian problem. That's basically what the topics are of these problems that I didn't do tonight. But as I said, I did them mostly last night. So there's a couple of gaps here, but honestly, I do think it's getting almost 10 o'clock. I think everybody should probably take a little break, and then depending how late you're gonna stay up, I think if you listen to me too long, the problem with that is, I mean, I love doing this. I could stay all night and be happy, but it's easy to get into a false sense of security, like, oh, I understand everything. This review is so easy. Dr. Annan's explaining, I understand everything he's explaining, but I need to give you guys time to really make sure you're solid for yourself. And then if you have more questions, you can stop by. I'm gonna stay till midnight. I'm also gonna come in tomorrow around 8. So I think that's what I would like to do, rather than just continuing. I've been going for already 3 hours. That's a long time. Yeah, Kim?
I have 2 questions.
Okay.
For the annihilator and the parameter, what like the common mistake that students make?
Common mistakes on annihilators and variation of parameters. One is using the wrong method. So if it's an annihilator problem and you try to use variation of parameters, not good. If it's a variation of parameters problem and you try to use annihilators, not good. So make sure that you are able to make that choice. Another thing is making sure that you get the annihilator correct from the table. I'm going to give you that table of annihilators. Does everybody remember what you do? If I have like f of x is 5x cubed plus e to the x, how do you get the annihilator of that whole thing?
You do each one.
You multiply the individual annihilators. That's another mistake. So you should multiply, even though this is a plus, you multiply those annihilators. So getting the annihilator right is very important, right? Obviously, variation of parameters, if you know this stuff here, you're going to be in pretty good shape, I think. I think that's the basic thing. Oh, I will tell you another mistake with the annihilators. Remember how when you go to the particular solution, there's a form of that solution? And sometimes I will say in the question, just find the form of the particular solution. Okay, if I do that, you just find there's like capital A, B, and C, maybe something like that in the answer. If I don't say to just find the form and I ask for the full general solution, a common mistake on this kind of an exam is a student spending way too much time trying to solve for the constants. So if I actually do expect you to solve for the constants, first of all, I'm going to make the problem come out really nice. It's not going to be a terrible process to solve for those constants. But if people are not doing their algebra carefully, you can take some numbers that were supposed to be nice and now all of a sudden they are very, very messy. right? And so then students start erasing and they say, oh, I gotta do this all over again. And then they spend a lot of time on that. And if I could only have told them ahead of time, which I'm telling you now, that whole thing of solving for those constants might get you a couple of points. It's not going to be a big game changer. Imagine if you spent 20 minutes trying to solve for those constants and maybe you got a couple of points out of that, and then instead you completely had to skip some other big problem because of that, because you ran out of time. People do sometimes run out of time. It's because they get stuck on these details that really aren't worth spending so much time on. Be willing to let go of some of those things, right? So I hope you can solve for those constants. We practiced it. We did group work on it. You saw me do some examples. You did the homework. But at the end of the day, guys, don't linger on something that doesn't really feel like it's about Math 250B. Solving for those constants is mostly just algebra. So I'll just leave it at that. That's my advice. Okay, great. Thank you. I am going to stop my recording now. Thank you for watching.